systems. So why do we do all this though? So one example is, was it AMS work, which is accelerated mass spectrography, and carbon dating is probably one of the ones which most people are pretty familiar with, by which we get some cosmic rays come into the atmosphere that spallate with nitrogen when they create carbon-14. Carbon-14's taken up by plants and things and eaten by animals or whatnot, and then they die, and we dig up bits and pieces, we convert that into a graphite, we take the graphite of the carbon content of them, and we put it into our accelerator, we convert that into a beam, accelerate it through, filter it out, and we actually count all the individual atoms, and we can kind of give you an idea of how old this thing was when it stopped taking in new carbon from the environment. Another example of that is we can actually take, say, the lipids of someone's eyes, which are some proteins and that only get formed when you're first born, and we can actually kind of estimate reasonably well what your date of birth is based off that information we can get. The other side of what we do is ion beam analysis. So in this situation, instead of running a sample all the way through the machine, we produce a bulk beam, and we okay, sorry, some message. We use that bulk beam to actually probe a sample, and we might be doing that because we want to look at what the effects are that take place when that beam strikes it, so we can look at the X-rays or the gamma rays and how the ions bounce out of it, or we can actually modify it too by doing implantation or using it to mix layers and things within the sample and do depth profile. So, and these are some examples too where we've used some of these various techniques. So on the left-hand side here, this is where we're actually doing characterization of microdosimetry, where they can actually use the beam of ions itself as an actual current that we actually can place into a specific space and region in a semiconductor, and we can actually look at the charge collection within that and kind of map out how effective those detectors and things are. And on the right hand side here, we apply another technique for the ion beam analysis, where we've done a lot of studies and works with aerosols, where we have samplers which breathe in around about the same amount of air that a person does in a day, and we look at all the very fine particle dust, PM2.5, PM10, and this plot down below here actually shows when Australia switched over from having leaded petrol to unleaded petrol, and actually looking at the amount of lead which was dropping out of the atmosphere due to that transition. So just touching more onto the control systems though of each of our facilities. So Antari is the 10 million volt machine. It's fairly explicitly an EPICS based controls that we have there, with a combination of various legacy manual aspects, which sort of came down to some of the philosophies in the early days. One of the challenges we have with tandem accelerators being very high voltage DC machines, transients which are caused during sparks, where we send out high voltage spikes and things. We had problems, particularly in the early days, to do with locking up processors and damaging electronics and various other things. So it's probably fair to say that the move over and the maturity of the various different methods of controls and devices used has been something that's taken a bit of time for us to sort of get closer to better integration of devices and that for doing computerized control. STAR, which is our 2 million volt machine, that comes with its own custom C14 OS, which was developed by High Voltage Engineering Europa, who we purchased the machine off. And we don't have a lot of control over it. We have been given the source code for that, but there hasn't been a great need to do much modification of that machine, though in the future we will be looking to replace the entire control system on that one and update the controls themselves. Sirius, the new 6 million volt, and Vega, also the new 1 million volt, they both came with the NEC custom AccelNet control system. It's probably more, the terminology of it is more probably analogous of the PLC world, where it works with tags, not PVs. And we're trying to go through the process of making up a interface so we can actually pass PVs back and forth, which mimicked in the tags in both systems. So we also have other IOCs and things running for looking after facilities information as well. Particularly, we need to log information for not just for the fault finding, but also for our regulatory requirements as well. So we have radiation monitoring, gas storage monitoring, and operators logs and so forth, which are facilitated through our EPIC system. So Antares, just a simple breakdown of the hardware. Antares has got still some legacy VME crates, which have gone through various stages of having the processor boards removed and various other interfaces put in place. So, but eventually we're hoping to move beyond all the VME, and we've been testing over. Andrew Downs has been doing a lot of work with switching over to Beckhoff PLCs for a lot of the field IO devices. We still have a lot of, and we use quite readily, the serial communications via terminal servers, so we can integrate those into the networks. The various platforms we run on Linux and Windows. Windows was required for the Beckhoff, and most of the obviously most of the Linux stuff for the EPICs, and we run typically 3.14 and 3.15 versions of EPIC Space currently. This is one of our CSS control screens, just to kind of give you a bit of a feel of what our operators see, and a beautiful screen put together by Andrew, who does some fine work. Star, this was our, as I said before, our custom screens, which were sent by High Voltage Engineering Europa. I think the videos really show you too much other than a few numbers flicking around. So that's the main interface for this accelerator, with its various different screens there. It's running on a Windows XP platform. We've had a lot of problems over time with transferring from, I think it was originally Windows NT, and trying to move through the different legacy hardware into the different versions of Windows has been big headaches and so forth over time. So hopefully something we look forward to getting rid of at some point. And the screen down here, this is just showing a little bit of lab view, just to upset a few of the real programmers in the forum. So we sort of can make up other various screens and facilitate some of the controls and information. This is more helping with some of the data acquisition, current measurements, and providing signals through to our older analog data acquisition systems. So as I mentioned before, so Sirius and Vega have both got the same control systems. This is what the AccelNet screens look like. To me, it looks very kind of a little bit more old school. It does work quite well though. That they've kind of got a bit of a clever scheme on how we can select and click and various bits and pieces, but same token, feels a little bit clunky at the same time. It's based more on a Postgres database, I believe, that pretty much probably doing as much as what I guess you'd expect most control systems to do, but it's keeping track of the various records and moving the information around in the tags, both for read tags and write tags, kept separately. And as I said, we've got an interface which we've been working on as well, which has currently got 12 IOCs, to try to bring all the facility variables or tags out into the EPICS environment, so then we can make it part of our archiving and so forth. So in our EPIC space, yeah, we've currently got 52 IOCs, mostly running between, actually 3.14 and 3.15 around our facilities at the moment. The broadcast domain that we've got is very flat at the moment, and it's part of our legacy of our initial steps in the EPICS, which started probably late 90s, early 2000s with Paul Tyler and Damien Lynch. So the EPICS broadcast domain is a little bit of a problem for us because it's between building 52, 53 subnet over the entire facility. There's approximately 400 PVs that we use, and only about 83 of them are archived. We're currently using the CSS archiving system. It seems to be a little bit of a headache for us in that if we do major changes to the structure, we seem to have to archive off the archive and then sort of rebuild new structures and things, which is a bit of a pain. We had a virtual, so currently Jian's been working on testing out a newer version of the Postgres database on a machine doing a proof of concept. And our previous two archivers are still running. One of them, which was running on a virtual machine, which was actually our first kind of step into the virtual space, just to try to see if this works for us. And we had the reliability that we've been sort of told about by quite a number of other labs who have gone over to virtual machines. And we've still got our older machine, which is still running, the older archiver, which we've just kind of kept them both running as a backup for each other at the moment. As far as facility monitoring, we've been running the Nagios which was only been the last few years that we've had that in place to start giving us more advanced warning on what systems are actually down around the facilities. I think we've got 43 devices that's currently in there. They all get pinged once every 30 seconds, and 5 minutes, and we get an error message if it doesn't reply within 30 seconds. So the importance of controls for us, though, I mean, this is even in the early 2000s, it sort of became obvious for a lot of the people in the AMS and IBA space that for electrostatic accelerators, some of the greatest improvements in the capabilities and performance actually came out from computerization of the control systems. The other big aspect was that typically people would make up a custom box of devices, and you might have signals which are dragged from one room to another room. So being able to go to a more distributed model where you've got more of a generic IO infrastructure in place, and also the need to not have to move analog signals all around a facility, gets rid of noise and also makes the standardization and the construction of those kind of boxes for control really much more cheaper to do, and hopefully more reliable too. So I think the only other message I'd say is, like, from the CAS point of view, please don't be strangers. Our doors are open for anyone who can visit under the current COVID-19 compliance matter, if they are ever allowed to visit from Victoria again, for example. And if you like any further information, we're more than happy to kind of get the Zoom and Skype calls up and going, and to really start to try to talk with more people in our local community. Thank you.
Thanks, David. You've used the entire 20 minutes, so unfortunately, I think we have to press on with the next presentation again, because we are already running, more than 10 minutes behind. So I think we can use the morning tea session for questions, maybe.
Not a problem.
All right, thanks. So next one up is Australian National University, and I think Daniel will be presenting for that one.
No, it's me.
It's Peter. You. All right. Thanks, Peter.
So will give us a chance to catch up with my talk. It's going to be a quick overview. So yeah, my name is Peter. I'm with the Australian National University here in Canberra, and we're running the Heavy Ion Accelerator facility. Quick overview of the facility. So we have an NEC 14UD, it's a tandem, 10 beam lines spread over 2 target areas, and a superconducting LINAC booster. Much like CAS, we've been around for a while, and previous to this, I think we were running a HV machine, and then even before that, we had a Van de Graaff accelerator, which met an untimely end in a fire. So this is our current control room. You can try guess which one's the the modern version. Of course, it's the one in color. So this isn't so much to say that we're running an ancient accelerator. It's just to stress that, again, as David was saying with ANSTO in Sydney, it is an evolution over a long period of time. So obviously we've got a whole lot more computers involved, but if you can play a game of is there a piece of equipment that's present in both pictures, and there is. So what's not obvious there is how much work has gone on inside those racks to extract all the old stuff and to install newer stuff. And we're on a never-ending program to slowly convert absolutely everything to computer control. But there are still some major, well-embedded functions that are still, run by a potentiometer with a cable running 100 meters. So for our control system, we're running EPICS, and we've been doing that since about 2012. Previous to that, we were running a homebrew Fortran-based control system. We're still running EPICS 3.14, and that's consistent across all our system, and that's basically a function of how we structure our system, which I'll get into in a sec. We've got nearly 6,000 PVs, including derived and calculated PVs. We're only running about 15 ISCs. We're still running 4 VME crates, and that is a legacy issue, and they were pretty much the only control points before we had EPICS. And since the introduction of EPICS, they've been incorporated into the current control system, and we've been slowly adding IOCs. Most of the IOCs that we've been adding are ARM-based TS7520 boxes, and at the time they seemed like pretty good value because you get a whole bunch of digital and analog and IO on board. So it was relatively easy to deploy. For actual IO cards, we're still using a lot of VME cards. We're still using a lot of Group 3 controllers and IO. And, in truth, they're pretty good and they're pretty robust. And, there's a whole interconnection with the loops are all interconnected with fiber. So there's, the impervious to noise. And we've also found that, in terms of value, in terms of how many analog outputs each card has, that's our best option at the moment. As I mentioned, we're using a lot of 7520 TS boxes, which are now defunct, but it's, we've already got them. And yeah, as I said, they've got a lot of data acquisition on board. As we introduce more IO, we've been heading towards using more Modbus units, and various types of Advantech brand units have proved pretty useful for us. We do also use AccelNet, but that's only for the AMS bouncing system. We did not want to let that leak into the rest of the control system, so that's isolated for a particular application. And we link a handful of EPICS PVs each way via fairly simple protocol. The way we have it structured, we have a central boot server, which is also our EPICS development machine and cross-compilation machine. And basically, that's where we create and edit all of the databases. The upside of that is that it's fairly easy to move things around and offload PVs to other IOCs if you need or anything like that. The downside is that sort of negates the distributed nature of EPICS, where we have one centralized server where all the IOCs boot their EPICS application from, they pull their databases from. So if we lose that server, we're fingers crossed that none of the ISCs have to reboot. We have a whole bunch of control terminals, generic control terminals that boot via LTSP, and some of those are radiation protection terminals, which I'll get to in a sec. And then we've deployed a bunch of Raspberry Pis around the place which run vacuum status displays just that are running on EDM. And as I mentioned, yeah, all ISCs boot from the server, which is good and bad. In terms of vacuum control, we're using a lot of FIFO gauges, which are serial, and they're plugged into serial to Ethernet converters and run on a in-house protocol, which it's worked pretty well. We've also started to use Infocon gauges, which, as far as we can tell, are just OEM suppliers to FIFO. And the newest version we're running is directly controllable by Ethernet or communication. So, and that's been pretty good as well. In terms of vacuum valve controllers and turbo pump controllers, we use those electronics boxes, those boxes filled with electronics. The current versions aren't connected to EPICs. They're not controllable by EPICs, but we do have readbacks on statuses. The reason we're still using these types of boxes is that we are a user-run facility. We don't have dedicated operators, and we do have a lot of academics that like to believe they know what they're doing. So they still like their switches and things like that. So we are developing a new generation of those boxes, but what we're also doing is incorporating ADAM 5000 units in the boxes. So they basically become Ethernet controllable or polable turbo pump controllers and vacuum pump controllers, while still allowing the operators the academics on the beam lines to, have a play with their valves and pumps. For control and readback, we generally lean towards protocol files. We don't really go deep enough to need to write drivers. We don't have hundreds of the same device. We also have some sequencer programs, but I don't know, I personally tend to avoid those because I find them very hard to debug once you put the protocol file in and the database, and so I stay away. The archiver that we're using is the archiver from Slack, which after a number of years is still version 0.0.1. That's running fine. We had our own in-house archiver, which I think, to be honest, the front end was a lot better than the Slack version. It's just that the back end with the PB record storage ran okay for a bit, but of course, if you're going to choose a SQL database, you have to really optimize how you structure that database. So once we started adding more and more PBs, that sort of fell over, and we've moved to the Slack archiver. In terms of a GUI, when we moved to EPICS, PyEPICS was chosen to as a control. So, there it is. We have I can actually pull up the actual one. So that's what's happening now, the accelerator. And we just move through different tabs for different sections of the machine. And I can't find a PB that I can change. I was going to say that one of the reasons I don't really like AccelNet is you got to type the numbers in manually. You can't use the arrows up, down, and change each decimal point like you can with, I think, most other GUIs. So I'm not sure. So it's still going. So we're still adding features in that GUI, and it's suiting us fairly well. The radiation protection displays are also written in PyEpics and, you know, similar things. And all these values are pulled into Epics as PVs, and then they get shoved into the archiver for our Panzer monitoring requirements. Vacuum status displays, we've got a few around. There they are. We've thought about moving to QEGUI and other things like that, but it's just the time that we need to move across, which I think we can all agree we're pretty time poor. In terms of the I/O, as I mentioned, we want to use the Atom systems. If you want lots of I/O, we're using a 5000 series. If you want some smaller I/O, a small amount of I/O, the 6000 series, you can just drop it in. And I think they've even got newer versions where you can daisy chain the Ethernet, so you can just keep stacking them on top of each other without worrying about how many Ethernet ports you've got. You just need the one. And our workhorse serial Ethernet converter is the what is it, EK something from, oh, there you go, EK 1524, and they've proved pretty reliable in our sort of environment. We do have some challenges with measurement. Now, it is a harsh environment. There are a lot of sparks, and there's a lot of electromagnetic energy flying about during sparks. So the challenge is how to, not so much how to protect the equipment to get good, reliable measurements without anything failing, because we know how to do that. We have electronics and I/O smack bang in the middle of the terminal, but that is a huge effort to get that level of protection. There are new metal shielded boxes, double shielding with the cabling and the entries. It's extreme. So the challenge is how to find the balance of keeping it easy but reliable, trying to find out where that boundary is. And the current challenge at the moment, we're trying to digitize accelerator currents, high energy tube columns, et cetera, and the way it's set up here is fairly reliable, but occasionally you get the occasional failure in that. But that's what we're doing. We're working towards digitizing everything, including our terminal control voltage. We'll see how that goes. So that's hopefully a quick overview of the controls at the ANU. Any questions?
Thanks, Peter. First of all, thanks for the interesting talk, and yeah, I'm still not sure. I'm also not sure why the archiver appliance has been on version 0.0.1 for probably 4 to 5 years or something like that.
Yeah.
They just keep changing the date of the snapshot, so I don't know. Hopefully, because I think a lot of facilities around the world are using it in production, so maybe they could bump it to 1.
Yeah.
But yeah, so you said that you have a few. Do you have mainly physical hosts for your IOCs? Is that correct?
Yes. So, I mean, there are applications where we could use virtual world. I suppose, I assume you mean by physical hosts, you mean actually.
Yes, actual boxes around the facility.
Yeah, generally, I mean, there are a lot of applications, especially when you're just communicating with the vacuum controllers, that you could just have it on a PC or whatever.
Yeah.
And again, we have ideas to do that, but you sort of go, well, it's running. I don't want to break anything.
Okay.
But that would be the smarter thing to do. Because at the moment, most of that's running on an IOC that has I/O that we're not even using.
Yeah, we had that scenario a few years ago, and then we moved most of our IOCs into the virtual world, and it's been going pretty well, and you can free up a bit of a rack space.
Yeah.
If that's an issue, I don't know if it is. But
Are you using Docker? Was it?
No, not yet. That's hopefully we'll look into that, but we're currently just using virtual machines as a VMware.
Yeah, okay.
And Linux containers.
And Linux containers as well, yeah, for the critical stuff.
Okay.
Yeah.
I'm keen to learn how you manage that, and how isolated. Anyway, we can talk later.
Yeah.
Just.
I'll touch briefly on one of my talks on that, but yeah, we can discuss later. Thanks.
I had a question for Peter. That you said some of your machines boot from your central Ubuntu server.
Yep.
I mean, although when you build an IOC, it's quite big. You don't need to copy much to the actual physical server for it to run. Have they got non-volatile memory you could deploy stuff to, so that they could reboot independently?
Maybe.
If that makes sense.
Yeah, we've been left with a system. Yeah, I mean, I'm personally trying to decide how we go about it. I don't like that central failure point. But having, being one of the people that upgrades and monitors it, I know what I have to do, which is why I'm interested to hear how other people manage tens of IOCs separately or whatever. How do you do that?
In our facility, we have a centralized storage, well, for the beamlines anyway, we have a centralized storage array where we have all the common software and the pre-built software that the IOC builders can use, but we also provide a mechanism to cache that locally on their host, be it a physical host or a virtual host. And then at least as the centralized storage array goes down, and it has happened, they're independent, they can reboot if needs be.
Okay.
So it gives them that measure of independence. We're still having the benefit of everything normally being available on the centralized storage array.
Okay.
And we have a script that caches the necessary data locally.
Yeah.
And they can rerun that. In fact, I think we have a cron job that reruns it on a regular basis.
Yeah, okay.
So that seems to work.
Yeah. Okay, cool.
Peter, it's Bryce here from the Synchrotron. The Atom 5000 engineering environment, what's that like?
Daniel here? Where's Daniel? Do you want to comment on that?
Don't worry, we'll follow it up later.
Yeah, follow it up later with Daniel.
Yeah, no worries,
he's theoretically online, but anyway, see if I can catch him later and get him to get back to you.
Thanks, mate.
Okay, we've got time probably for, we've got time for one more question if anyone has it. Otherwise, let's move on. Thanks again, Peter, for this presentation.
All right. Thanks, everyone.
So next one up is Nick. Nick from the Australian Centre for Neutron Scattering. Thanks, Nick.
So, can you all see my screen?
Yes.
Excellent. All right, so I just need to flick a few things around so I can see my own stuff. Beautiful. All right. Okay, thank you very much, Andraj and David, for organising this, and whoever else has been working behind the scenes. So, yeah, this is, I love this sort of stuff, having these sort of collaboration events, and I'm really, really glad this is taken off. So I'm just going to give a bit of a retrospective. So I'm getting old, so I like reminiscing. So I'm going to look back on a little bit of the stuff that we've done over the last 18 years of doing controls. at ACNS, so the Australian Centre for Neutron Scattering. And so one of the principles that we started out with back in 2002 was that we wanted to work with controls, electronics and software where we didn't reinvent the wheel. When I first came across this controls in the early 2000s, there seemed to be a lot of people doing the same thing over and over again. And so we endeavoured to try to use commercial off-the-shelf software and hardware wherever possible. In the early 2000s, there were a bunch of synchrotron and neutron facilities that were building products, and such as there were products called Sadana and GDA out of the Diamond Light facility. And we were building a product called Gumtree, and all of these products were basically doing the same things. One of the problems back then was that, or mistakes, was that facilities tended to talk about their products only after they had developed them and they were relatively mature, and they were then happy to go to a conference and say, look, we've built this new piece of gear, this new bit of software, this new bit of hardware, and generally there wouldn't be all that much collaboration generated because everybody else was doing stuff in parallel. So I think today we're in a much better state, 20 years on. The mistakes of the past seem to be, we've seemed to have learnt from our mistakes. And it's encouraging to see that, for instance, in the neutron scattering world, the European Spallation Source is adopting and improving existing products rather than trying to build their own stuff from scratch. And I think another reason why it's easier to collaborate, especially on the software side, is things like GitHub. So, and it's certainly aided the process of collaboration. And probably the best examples of collaboration is the wide adoption of Epix and Tango as device servers, and except we don't use them. So we're kind of we're on the fringe there because we've adopted another standard with another facility, which I'll go into a bit more in a later slide. So just quickly, we are kind of different at ACNS to the rest of the folks on this conference, in that we actually we don't use accelerators and we don't use epics. So please, everybody, don't go to sleep. There's still something to be learnt, I think, from our experiences. So just quickly, our source is for our neutrons is Opal, which is a 20 megawatt multi-purpose reactor. And as you probably know, it's apart from generating neutron beams, its reason for being is the radioisotopes and medical isotopes like molybdenum-99. The silicon business, which does the silicon wafer or silicon ingot transmutation doping to create phosphorus, so you get evenly p-doped silicon, and neutron activation analysis. And as you can see in the slide, the Opal is an open pool reactor with a compact core, deuterium oxide moderator, so heavy water, and it runs on low enriched uranium, which is important for nuclear non-proliferation reasons. The reactor went critical in 2006 and has been in operation since 2007. And Opal runs 300 days per year, which is the highest number of days per year of any of the research reactors around the world. And we are running user experiments those 300 days per year. So our instruments need to be highly reliable to work on those sort of timescales with limited amounts of downtime for maintenance. So as I mentioned, we're not accelerator based. We use neutrons as our probe rather than X-rays. And but I've put a little slide on the picture on the screen there to show one of our sister facilities at Oak Ridge, which is actually an accelerator-based neutron source. So that's my hook into accelerators. So yes, you can generate neutrons from accelerators, and you can use a mercury or a tungsten target. And but the controls that we're working on are not accelerators, but more the end stations, which I will show in the next slide. So so this is basically the area of responsibility for ACNS, is the 15 instruments that we run and the user program that we run. And the 15 instruments are divided up into two guide halls. So rather than in a synchrotron case where you have hutches around a ring, we have these sort of large open plan areas where we have the 15 instruments. And we have a couple of international partners. So in the reactor beam hall on the right is the SICA instrument, and that's the Taiwanese that have funded and managed that. And also on the far left is SPATS, and that was bequested to us by a German neutron source that shut down recently, and we set up one of their instruments here. All right, so for me, people are actually more important than technology. So I'd like to acknowledge the groups that have had a big influence on what we do. So there's a community called NoBugs, which a few of you probably have heard about. And so that's basically all about end station controls software and also a bit of data reduction and analysis. There's the ICOLAPS community, which is more accelerator based, and the Nexus community, which is a data standards community. So, so since I started at ANSTO, I've been big on the whole idea of collaboration and standards, and we've put a lot of effort into these communities, and we continue to do so. So, so even this year, we're entering into a new collaboration with the European Spallation Source on a data acquisition software system, and also with Oak Ridge National Lab on a data acquisition hardware system. So, and the way that we think about controls for our beamlines is inherited from the Nexus community, which has provided a data structure, and the way that we structure our controls is based on that hierarchical structure of the Nexus files. And so all that I'm presenting here is the hard work over the last 15 years of the group of people that is on this list here. So today, we currently have the 15 instruments, as I showed in the previous slide. We have 4 electronics staff and 3 software developers specifically for controls. In a slight departure from the synchrotron experience, our neutron detectors, for example, may have production runs of only 1 or 2 units. And may be supplied with or without their data acquisition electronics. And so in our case, we need to be able to manage detectors from across the whole gamut of technical techniques. So so we, at ACNS, we fill the detectors with gas. We do modifications of the detectors themselves. We do repairs and maintenance on the electronics, and then development of data acquisition electronics and the control electronics that sit on top of that. In our journey, Gumtree was the only piece of software that we actually wrote in-house from scratch, and this is basically our beamline controls software. So think of it as one of the Epix systems, which the Epix UIs that you can stick on top of Epix, like CSS or whatever. The concept of the Gumtree product itself was unique at the time, but has been adopted by different people and implemented in different ways, but still basically the same concept, and that was try to integrate experimental design, to aid people with scripting without having to write everything from scratch, instrument control, status, data reduction, visualization, and have that all in one package and well managed in terms of window management. So Gumtree itself, it's a Java app with using the Eclipse rich client format, and we like to claim that we were the first to use the Eclipse platform for in the science domain. So Gumtree has two major components. It has its rich client, and it also has a server mode. And the server mode we use for providing web status of our instruments, server-side execution of the scripts that we use to run the instruments, an instrument notebook, and we can do data reduction in the browser. All told, we have 3 products in our software suite. So this Gumtree UI, we use 2 products called Six and Histogram Server for our device servers. So Six is kind of similar to Epix in that it is a device server. However, rather than the one-to-one correspondence that you have with Epix for a device, there's no limit to the number of devices that you can have in a single instance of Six. So Six is written in C, and it has a TCL and Python interpreters, and those are used for sequencing the devices when you're doing an experiment. The other product, the histogram memory server, is the device driver specifically for our detectors, and provides real-time data processing and visualization. And both of those products we have developed in collaboration with the Paul Scherrer Institute in Switzerland, who actually built these products 10 years before we started using them. Just a couple of little lessons learnt. So over the years, my first lesson, which I learned the hard way, was that activity doesn't equal productivity, and I made a classic project management mistake of throwing too many people in and not providing enough focus and organisation for those people. So we've found in the long run that it was better to have a smaller team and people focused on products, and also that our products had simple but powerful APIs. And so we have worked really hard on making our products simpler, and we continue to refactor our products to try to provide as much abstraction as possible. And we've also put a fair bit of effort into writing code generators, and that has significantly improved our productivity. The second lesson learnt was that we were told early on in our development, when everything's moving along at pace and we're trying to start a facility and start a user program, that it was taking too long for us to develop our products. So in simplifying our APIs, we also made all of our APIs scriptable, and so we ended up adding Python as our major scripting language, and this helped a lot. So we can script a bunch of things, and this has become commonplace now. This was fairly new when we were doing it 15 years ago. So we can script our UIs, our buttons, we can script our workflows and our tasks, and we can script our data reduction, our plotting, our visualization. So one of the lessons learned was that with the Gumtree product, for example, that our mindset was firstly to build a platform. Our mindset then changed to supporting the product and helping the scientists run their experiments efficiently, and Python was the key to that. Another key to keeping our team sizes small was standardization, and I was heartened to see Alan's talk and seeing that the PowerBrick standardization. So I was part of the early phase of that standardization process when I was working down there at the synchrotron. So, you know, we've ended up with motion control based on Galil. I'm glad you've chosen the PowerBricks down at the synchrotron. And just noting that one of the big differences in the way that we think about motion control at our facility is that we've got lots and lots of heavy stuff. So we're very conscious of inertia when we're moving around tons and tons of gear. But as you can see, moving from left to right, as we move more towards the science domain, we have less and less standardization, and that's because scientists like a certain type of product to do their data manipulation and data processing, and so that's fine. But we're still working towards trying to standardize at a higher level in that area. One of the things that we also found useful was to have a common data model that we worked on, and a lot of this is influenced by the Nexus community, and this certainly helps us a lot in terms of the standardization of our data processing type applications. So one of the things that was an innovation for us was our multi-sample workflow, and so this significantly aids the automation of experiments, and one of the strengths of it is that it provides for the type of experiments where you need to be able to associate files between different parts of an experiment. We generate an XML file that does all of the file associations, and then you read that file association into your data reduction software, and you can automate all of that. So we've been thinking in terms of workflows. The take-home message is basically try to automate through using the concept of workflows. So this is just a UI for that particular part of our product, multi-sample workflow. So I'll just gloss over that quickly. The other thing that we do is we nefariously gather instrument statistics from our software, and this talks to the utilization of instruments, so we can see how long the instrument is idle and how long it's actually doing experiments. Don't tell the scientists. And yeah, talking to this point about virtualization and containers. So yes, we've been working in that space for quite a while. We are primarily, we're using virtualization. We're only just embarking on using Docker containers, and we're finding that useful, but it's not without its a lot of issues. And so we're maturing in our knowledge of it. We don't have the Docker stuff in production as yet. We've got it on one instrument, and we're still trying to work out how to use it properly. And in terms of our VM stack, we also use Puppet to look after the configuration of all of those VMs. And I noticed that David brought up Nagios. We're also using Nagios. We had the great privilege of hosting ICOLAPS 2015 in Melbourne, and that was one of the high points of my career. And I'm so thankful for the Australian Synchrotron for putting up their hands to host that, and that was a fantastic event. And that's basically the end of my talk. One day we will probably cut down the gum tree and chip it and put it on the garden. But we're watching in earnest as the European spallation source, which is the newest spallation source in the world, the newest neutron source in the world. They're working on a project that uses EPICS, and so and they have a similar product to ours, our Gumtree product called Nikos, and we're interested in seeing where they go. In terms of our current stack, we're still not where we want to be. We want to more widely use Jenkins, unit testing and system testing, constant integration, continuous development with GitLab. We've got all of this in part, but we need to provide greater coverage of all of those things. And we don't expect that we will be able to do this within our current resource limits. So in terms of improving our software processes, we are hoping that at some stage we will build a second guide hall. So basically double our capacity for the number of instruments. And as part of that program, we would be looking at our practices and have the resources to be able to update all of those things, and possibly in that context be rolling out EPICS and some other UI to run our instruments. So thank you very much for listening.
Thanks, Nick. Yeah, it's really good to see that. I mean, I like your approach of adopting standards and creating collaborations and just working with other people on the same project or same product rather than trying to develop everything in-house. It seems to be working really well for you. So yeah, I think I'd like to hear a bit more about it at some point, but it's definitely good to know that you're doing it. We are well and truly into our morning tea break. So let's maybe extend it to like 5 minutes past 11, but maybe not longer than that. So that should give us time to ask questions to Nick, Alan, and David. And to grab a cup of tea if you want to. So everybody feel free to turn your cameras on and microphones and start talking.
Thanks, Andrzej. I had a question for David, if he's there.
Sure, yep.
Yeah, I'm curious, you mentioned, was it the lipids in the eyeballs? You could get a good estimate of someone's age?
Yes.
I'm wondering how good the estimate is.
Sorry, how good is the estimate?
Yeah.
Bring up the chart that I got off. Just see if I can bring it back up. It was work that Vladimir Lovenos was working on at ANSTO. So let me just share this if I can.
I think C14's half-life is like 5,600 years. So it's you'd probably be able to work it out maybe to within half a decade at a guess.
So, I mean, you can see the error bars they've got on there. I mean, they're particularly in this part, they're looking at the from the bomb pulse. So one of the wonderful things that happened when they were testing out all the nuclear bombs after 1945 was that they produced all this extra carbon-14 atmosphere and in the environment. So there's this actual pulse of extra C14, which they can utilize for doing this dating. So you see around like 1960s and that, they've kind of got like the actual date of birth here and then the range on those dots. So yeah, so obviously around about the 80s, 1980s, and then it starts to get a little bit rubbery, but it may have been just the samples they had at the time. Yeah.
Okay, thanks for that, Dave. I like your Dalek.
Thanks, man. Actually, if Peter was there, I was kind of interested in those interfaces you guys have on the I/O. It looks like you've got some kind of custom set of electronics to try to get rid of transients and various other things coming into the system.
Peter's not there at the moment. Can you guys hear me?
How to be buried
it is essentially just
in a diagram so we can implement a.
I think I muted Daniel. I'm not sure if there was a lot of noise coming from him. Did I mute everybody?
Yeah.
Sorry.
Yeah.
Yep.
It's all right. And it was kind of interesting. I think Alan was saying that you class like 11 years as kind of the, is that the typical life cycle that you try to look at renewing or certainly reevaluating the controls and devices around that kind of period of time?
Yeah, well, actually, 11 years is a long time for electronics gadgets. And I mean, the cycle is actually getting shorter and shorter. If you buy a gadget today, I don't believe that the support will last that long anymore. Okay, but certainly in the past, all the controllers they certainly have a lifespan that longer than 10 years. But we are finding that a lot of the controllers they are slowly getting aging. They need service anyway, and this is a program that we do every year. During the shutdown, we will either have a look at each one of the controllers and we either pick them up and refurbish them. But however, we are starting getting the notice from vendors that those are getting to end of life. They usually typically give end of life notice about a year ahead, and they will still have continual support for maybe up to 10 years sometimes. Okay, right. But it is all with the will of the synchrotron moving across to the power brick. We tend to like to take the opportunity to upgrade them, and if possible, and of course that goes with whether you have the budget as well to do it.
Yeah.
Otherwise, we will persevere with the existing equipment, and that means that you need the skill set to actually refurbish them and fixing them.
Yeah, we just went through a rather painful process with our old AMS data acquisition system, which is based on a VME 6800 Motorola processors, where we pulled out the spare board and goes, last tested okay, 1995.
That's very old.
And then we had all the old SCSI and various other things. So, I mean, between the group of us, I think did a remarkable job trying to get this thing with modern equivalents and whatever else, but we still had to buy in through the nose for an old card for a very old processor to make the whole thing work.
Yeah.
Actually, the other side from hardware, what about things like operating systems? Like, as I said, we've had obviously the pain going through the different versions of Windows, but you guys are largely Linux based and so forth. Is there any kind of particular program or method that you've moved forward in your various different versions of operating systems?
Right. What we actually done is that we noticed that every time that we're upgrading an equipment, like for example, you mentioned about VME, and it's a large board. In fact, today with the modern electronics, you can probably do a one VME board in the chip, and that's the problem. And you probably will find that power saving and also cooling requirement is vastly different. and also the real estate as well. So it drives you to upgrade. And when you do this, obviously on the software side is changing as well. So all the modern OS don't usually tend to be backward compatible, okay? So what we did was that we want to make sure that the vendor, whoever we want to engage, will have an idea of what we have available on site. And so we actually put together a document to basically list out all the standards and equipment and software-wise into a document. So we're moving forward to tendering process. We're embedding this into the tendering process, where we actually send this document out to make sure that the vendor knows what we're using. They still have a choice to offer their version of the modern equipment if they want to. And during the selection process, it will get filtered out. If we really want to keep up with legacy support, then we will probably choose older equipment, but or the one that we're using. Or if we want to move forward onto the cutting edge, we can actually have a choice of using the new one. And so this document was very important for us. Yeah.
So given that you're mentioning tenders, so these are like for pretty big purchases, for big major projects, not done on the sort of smaller individual system level.
Yeah.
These are big sort of brush strokes across big, large areas of the facility.
Yeah, I mean, we do refurbish smaller things. Like, for example, I think that recently there was a talk about replacing a VME version of a data acquisition system. Seriously, that system is very antiquated, and it runs on the VME board, and the OS probably is dated back 1970 or something, and it's getting harder and harder to support that kind of thing. And you really have to say whether we should just buy that new single chip system.
Yeah. It's
Yeah.
funny you mentioned that. I think one of my last slides towards the end of today, I've got this Arduino kind of chip, which is basically that two processor boards in one. As you said, like the whole thing and everything just rendered down to one chip, one development board.
In my past experience in developing electronics, I had the opportunity to develop an FPGA system. It was a correlator, and we were using initially we're doing design on the Vertex 4 FPGA, and it was costing around $2,000 a chip. But the big problem was that the ongoing power costs and also cooling costs was almost amount to $100,000 a year. And
you went 2 years Bitcoin mining, were you?
Yeah, well, no. We actually, I was involved with the CSIRO radio telescope in Western Australia, the ASCAP project, and we built that system. And then in 2 years, technology has changed, and we actually half the power, half the cost. I'm talking about the real estate as well. The actual physical real estate is half, and so because of this, we decided to actually find money to support it, and the ongoing operating costs have dropped dramatically because of that. Okay, but they obviously have to have the will from the management to do this, and we argue for a long time, but that's exactly the end result, which is very good.
Yeah, very good. Thanks for that.
Yeah. Okay. Anyone have a experience on end-of-life projects like that, or anyone interested to ask any questions that I might have on the slides that I presented?
Just a kind of general comment about in-house development of electronics, and you touched on FPGA development and all that, and this spills over into evolution of language, programming languages, evolution of design methodologies and so on. And one of the biggest problems is, of course, getting people with the appropriate skills or skilling them up, which leads to, in many cases, very long development times and cost overruns and all the rest of that, and ongoing maintenance, because it's it's nice to spend a couple of years developing a nice FPGA design, but then you've got to have someone who understands how it all hangs together and how to use the tool chain to maintain it, all those sorts of things. So in a way, although it might sound a little bit frivolous to talk about things like Raspberry Pis and Arduinos and so on in our critical instrumentation chains, but they are so easy for a person to pick up and learn about how to use, mainly because of all of the community contribution towards it.
Mm.
The difficulty with obscure things like FPGAs is, whilst there's a huge amount of money behind it and a huge amount of development time spent on it all around the world, the community of people who can ask and answer questions about how to use it is much more restricted, because it's a much more commercial sort of project, whereas things like the open community stuff is not so much.
Mm.
It just seems to me that, and even there, I mean, talking about FPGAs, there are open community forums for FPGA development, but most of what they like to discuss is how to get away from the locked-in tool chain that people like Xilinx and so on want them to use. Yeah,
you're correct. Design Common, for the Arduino and all that is actually have changed the world. And a lot of the scientists and engineers using them, I think is great, because they're sharing all the code. And there's a vast, applications around those kind of, simple device, which is, or simpler device, I should say. But FPGA is complex and it requires special skills. But there are certain things that those Arduino cannot do.
Oh,
the vast high-speed processing will require, like for example, the radio telescope project. We are talking about 7 terabytes of data, 7 terabits of data per second coming out from 36 radio telescopes, and you need to halve that data and squeeze it into a fiber optics. You cannot do that with a Arduino, and so that's why you have to go that way. But yeah, it does require a lot of engineering, and the thing is that one thing I learned is that through the whole process, you really shouldn't stay behind the cutting edge. Because once you take such a long time to develop those things, by the time you finish your product, your end product, you are actually no longer the leading edge. So you have to start with the bleeding edge chip. And by the time you finish, you expect that you are just behind the cutting edge. And so you still can use it successfully.
Yeah, I definitely don't advocate using low-powered toy devices for everything, because, as you say, it simply won't work. However, there are things, in many cases, data acquisition, which we don't require huge data rates and so on, and can be handled by. I've heard people comment that, what's the point of relying on something like that when there's no support for it, and that the thing won't be available in the same format in the next 5 years or so, all of which is true. However, they're simple enough that you can redo them in the current format. Whereas trying to do that with something like a high-end FPGA is just not going to work for you.
Relatively cheap, like a Raspberry Pi or we use a couple of red tires. They're cheap enough that you can afford to have, a couple of spares kicking around.
Yep.
Later in this afternoon, my presentation will compare this performance between the FPGA CPU and GPU, and just address why and when we should choose FPGA. Yes, as just Terry said, for the Arduino or the Raspberry Pi, it's just for a very low-end, slow bit rate application. And in the middle range, in the middle scale, maybe CPU is a better choice. But for the ultra large scale parallelization application, FPGA may be just the only choice. I will address it. I will explain it later this afternoon.
Yeah.
What we need is a high-speed device or high-speed devices with the same sort of community support and the same sort of easily prototyped approach that you on those devices that you get with the low-end devices. There's all sorts of impediments to doing that, I'm sure, but the major one, of course, is learning how to use the development tool chain, which is the major advantage of, take Arduino as an example. The major advantage of that is you start an application and immediately you can download code to your board. There's hardly any tool chain involved at all, and what there is very easily understood and basic. Whereas something like the high-end FPGA development, the tool chain is obscure and in many cases buggy and quirky and slow. You can easily drink too much coffee doing FPGA development because you wait so long.
There's no such thing as too much coffee.
Yeah, that's true. Yes, just for the CPU or just you say Arduino is the MCU. Yes, you can directly compile and run it in minutes. But for FPGA, you may take hours, even a day. For large, you may take
it's even
time for compiling. Yeah, it is true, but it's just you have no other better choice. That's it.
Yeah, unless we develop platforms that allow themselves for that quick prototyping, because it's getting to the point now that if a person hears the word compile in the tool chain, and they come from something like a Python background, an interpreted background, they'll say, no, I don't want to use that. Compiling takes too long, or maintaining the libraries for compiling is just too hard. So they'll immediately turn away from it.
I think people are overly cautious about compiling these days. I think if they run scared, oh God, I've got to write some C code. And rather than write 10 lines of C code, they'll write 100 lines of stream device code. But it's not code, so that's okay.
Yeah.
I mean, don't get me wrong, I like stream device, it's good, and Python, but I think, and especially managers, I think, developing C code, that's going to take forever. But they'll spend twice as long developing non-code code. It's a configuration file, that's not code. But it takes twice as long to get the configuration file right.
But what is it what is it that you think scares people about that? It's not because it's not the code writing. The syntax is well understood and well supported. I think it's the library maintenance.
Maybe it's using libraries. I suppose, and maybe yes. I don't know.
And the strange thing is, of course, that if you prefer Python, you've still got library maintenance in a sense. You've got module maintenance. You've got all the vagaries of pip to worry about.
Yeah, and maybe with Python you don't get those linking errors till runtime when you call a method that doesn't exist. And in a sense, you're putting off the problem till later on.
That's right. It's even worse then because it's harder to.
I think there's coverage tools that can help with Python, but you never know.
Yeah.
I don't know.
I think it gets back to tool chain. The easier a tool chain is to use.
Oh, definitely, yeah.
The more likely people are to want to adopt it, and this is why things like Arduino have succeeded.
Yeah. I'd just like to add that, as much as I'm a convert for FPGA because I worked with them for quite a while, and it does cost a lot of time and money, especially when it comes to a particular IP. The silicon fabric on the FPGA require that you need to purchase a particular kind of IP, like, for example, a DDR RAM module, for example. You can buy them and say, so you can work with DDR3 and all the way up. If you don't buy them, you can download a design common version, which is only work with DDR1, okay? And it hinder your progress on the high-speed applications. But however, there is a chip that is available, that is commercially available, very cheap to buy. I'm talking about GPU here. Is been a favorite by a lot of the high-end computing people, and the reason is that this thing is being pushed along by gamers and is a commercial product, and your investment is just in code, and you can just plug this card inside a PC, and you suddenly have a benefit of 1,000 GPU helping you to process things. And if you don't like it, when the next generation, which is about 12 months away, and you double the number of GPU available for half the price. And this is something that is been evolving with NVIDIA. Is a very good space to watch. In fact, that in the radio telescope project with the correlator, there is actually a version of a GPU correlator versus the FPGA correlator we built in Western Australian University. And it's just as successful. And the power consumption is also comparable to the FPGA. And so GPU is worth considering as well.
And another point is, maybe if you consider the FPGA solution technically better or more elegant, it might be just quicker and cheaper to buy 3 or 4, 10 GPUs equivalent and just program them really quickly. You can maintain them very easily. And I mean, I've got 10 of them, but it's what you save in development costs and maintenance costs may outweigh the extra cost of buying 2 or 3 or 4, 10 units.
Yeah. The NVIDIA GTC conference just happened about a month ago. And the thing is that if you keep your eyes on in that space, most of the libraries get updated regularly, and the performance is double all the time. And I think it's worth looking into that. And what I also found that the investment in software that you wrote in the previous generation GPU is perfectly portable across into the new generation as well. In fact, you'll find a level of acceleration happens with the additional GPU hardware. So it's a good investment space to look at in the GPU.
Yeah,
I think.
Sorry, guys, I have to jump in. We should get going with the next session. We're a bit late. There will be a long lunch break, so yeah, we can continue with the discussion during that. Okay, so the next block we have sort of miscellaneous topics, a bit of everything, a bit of standards, a bit of technologies, a bit of processes. But we're starting off with David again on the development of standards for CAS. David?
Thank you. Okay, I'll just, hopefully my laptop's calmed down now. So I think it was actually pretty evident for just what just happened in the break there. Everyone can see that. Okay, so what I was hoping to sort of share today is just more something which was going on in our group at least, and I'm sure this is probably reflected amongst a lot of facilities as well. I mean, a lot of people probably talk about standards. Some people hate them, some people love them. I know we all. And I think it sort of starts to create that divide between what's this kind of sandpit time and what's going to be kind of implemented around facilities. So, why are we kind of giving this talk today? Well, I mean, we sort of wanted to move towards a better kind of standard arrangement for our facilities. And I think, as we kind of mentioned before, we've got such a long period of time and we've inherited so much legacy from the past. It's kind of created so many headaches for us that we wanted to have a much better kind of handle and a better structured way to approach things. I mean, that's also been because we've grown over time too. We've gone from having the one facility, which in this case was the 3MV, to the 4 machines we've got today. One of the symptoms that we kind of see in here, and I kind of call it also like the technological expanse, because we've got technology which has gone right back to the 60s through to modern time. It comes with its own challenges as well. And I mean, there's certainly going to be things that we have to support which they don't have equivalents for today. For example, the the main device which is used for regulating the terminal voltage on our accelerators is based on a vacuum tube, where we're kind of surviving on ones which were manufactured in the past that we can no longer get anymore. But at some point in some future, there's going to have to be development to kind of replace those. So some of the things which create these challenges around, you know, what technologies was used and how people approach things in the past is we've got, in our case, the lifetime of accelerators can branch across many decades. Our facility, we've probably had so many technical and scientific crews of people who have had turnover over multiple times over the lifetime these facilities. We've got the ongoing pressure of ongoing capabilities development within the facilities, sort of needing to install new things and add to things and modify what's there. We've got the technology which sort of become available or has matured and what's on the marketplace. And I think, as we were sort of discussing in the break there before, things which have reached end of life, even that the manufacturer no longer supports, or they've moved on to new technology, so it doesn't exist anymore. And also just the fact that the sheer volume of different choices which are out there too. Yeah, so discontinue. Also, likewise, regulations may have changed, which changed the way that we have to approach things and build things. Standards that already exist. I think people who are, say, from the electrical background are sort of very used to working with something like the AS3000 standards that we must do for electrical work and so forth. And then the engineers who are working on vacuum systems that are probably having the issues to do with pressure vessel regulations and various other things. One of the things, and this is, I'll be very interested to hear people's opinions on this actually, is I think a diverse team can also kind of lead to diverse solutions, which means we can kind of, means we've got a lot of good ideas, but we have to kind of somehow kind of distill that down into hopefully one or two good sort of reliable solutions that we sort of kind of move on with. So, I mean, from a business kind of, if you look up like a business definition of standards and why, I mean, I think it's all very self-evident. We can't build systems and buy things from a marketplace unless they kind of comply to some basic level of standard. And we can't sort of rely on a certain level of quality unless I think these photos here of these buildings around Santos, where apparently down by the beach side, they weren't really too excited about using the proper way of doing foundations and various other things. So all these buildings are all sitting on weird, wonderful angles down the beach in Brazil. And likewise, being able to talk in the same sort of languages. So, you know, I believe there was some stuff up in the early days with the shuttle programs where some people were working in millimeters, others were working in inches, and it was causing all kinds of problems in the translations of trying to communicate. So, I mean, reducing costs, the efficiencies, mitigating risks, consistencies, confidence, and all uniformity, all these things, yes, I think they're all very self-evident. And, you know, most of the programmers here today wouldn't be able to do programming if they didn't sort of conform to a syntax and various other aspects to make that all work. So we all engage with them to a certain level. I guess it's a case of how deep we go. So, but from a practical point of view of where I, you know, myself and a few of the other people sitting in the city, where in the facilities in CAS, we want to see a mutual understanding between group members, how we kind of look at things. We want them to be serviceable between one or more staff members. We don't want to have these, as I put down the bottom there, unicorns. For a long period of time, we'd have like a beamline that one person built, and only that one person knows how it goes together, and one person knows how to service it. And that person retires, or they become sick or hit by a bus, and we're kind of stuck, and it has caused operational problems for us in the past. And I think predictability is probably the biggest. I've highlighted that one because I think that's probably one of the more strongest aspects here, that we want our facilities to be as predictable as possible. We want to know what they're going to look like. We want to, if we're approaching it to do any repairs or modifications, we want to be able to anticipate what we're working with too, if it's been built to a particular standard, or that it's been considered in that way, that it's uniform. Also, by trying to develop a written down level of standards too, it helps us with the knowledge transfer. If we bring on board new staff members or bring them into the group, or even have to have someone work with us, having something we can actually show people and work through with them really helps facilitate that transfer of knowledge, we feel. And as I say here, simplification of range of solutions that we have to support, automation of processes where it's possible, and reproducibility, which is supported by the quality systems as well. So I mean, down the bottom left hand corner here, this is what I'd kind of call one of our unicorns. Someone put together a vacuum controller. They were kind of electrician background, so they decided to make everything in a whole bunch of relays and tried to kind of make a relay ladder logic kind of arrangement, which effectively we had to, as soon as we had problems with it, we had to bin it and replace the entire thing. And I think this is kind of summed up a little bit in the whole way of, like, there's many ways, as I say, many ways to skin a cat. This is kind of like a flip-flop. You could approach it depending on your kind of background, mechanical person, you've got someone who's old school with valves and that, digital electronics, coding, relay-based, electronics-based, and microcontrollers, and even Lego blocks. So I think often it's not the case that we can't come up with a solution. It's and this is the kind of issue about the diversity solutions, and which can be greatly influenced by the kind of backgrounds of people who come in. And I think that does kind of bring some level of difficulty in how groups can operate, particularly when people do sort of come in with their own background and have their own particular flavour on things, and how that kind of impacts into this pool of unicorns that we might end up with or herd. So that said, I think when we talk about standards, we have to kind of look at it with that we've got good intentions, and when we're trying to bring it in, I think that's definitely the way that our group has looked at it. I mean, as I put this little thing here to break people's eyes, I mean, depending on which way you want to look at it, you can sort of see different things. But we don't see them as, a tool to kind of crush innovation. We hope that people can still have ideas and still have a little bit of sandbox time to try things. They're not a comment against anyone's competency or expertise, not to undermine anyone's value or security within the group, and not to take away anyone's input or suppress anyone's development. And I think that's kind of hopefully self-evident by people coming along, even in today's thing. You're all watching this presentation, sitting in front of your screens at the moment, and hopefully hearing the ramblings of many other kind of people as well, to sort of help expand knowledge and understanding on things. So we've created within our quality system this, we've called the design and construction guide. The areas in which we've tried to cover, and this is a living document for us. As much as I say it's a standard, it's living in the sense that we're kind of adding to it as we go along. So we've been able to capture some of the information about electrical, information technology, control systems, vacuum, compressed air, chilled water, radiation, racks and cabinets, labeling, painting, as it sort of goes on, because these seem to be the areas where we're having a lot of crossover of different people working, certainly within our group. One of the things which also helped kind of catalyze this was we resisted for some time, and I kind of hate what I'm about to say. It was actually probably not such a bad thing that we've moved into a SAP maintenance-based system, which kind of facilitates when people put in jobs. And part of that move over, we had to actually identify all our areas in we selected the process of functional locations. So all the parts of our facilities are kind of described through these functional locations, which I've got a more detailed list here. And this started to straight away unify a little bit of the way that we sort of talk about the facilities and start to give us a common language. So just to kind of, just touch on a little bit further. So within that document, the areas that we which encroach on for the controls area, we've got information there about how we're assigning our IP addresses, host names, domains, labels, all the different kind of communications identifiers, network and password management. And likewise, one of the ones I'll probably talk about a bit more is like how we approach PV names now within our facility. So as I said, we're trying to make our PV names prescriptive, and now how we're sort of building those is we're building those around the functional locations names. So we can actually use the equipment tag, which is its functional location, and then attach the parameters onto that. So when we look at the ones down the bottom here, we can straight away see that, okay, we've got the Sirius accelerator, the IBA beamline 5, beamline 1, and we're looking at beamline valve 1 and the status control for that one. Likewise, we can look at the Antares accelerator, the main actual accelerator itself, high voltage generator, the terminal potential stabilizer, and we're looking at the grid voltage readback. So these are very readable now to a number of us in the group, be as working in the electrical area, the mechanical area, or in the controls area. Just to kind of compare, like these were some of our PVs from the past, and it was very much kind of the legacy of the Wild West, and whoever was decided to program or build up the Epix records sort of came up with their own kind of flavor as they were working on things. So some of these, it's very hard to kind of decipher what they are. I think C14 beamline, I think maybe some kind of high energy Faraday cup, but they didn't lend themselves to being very user friendly or that the rest of us could sort of work with. So we're hoping this model will unify across more than just the control space for the rest of us to understand. So just to give you a bit more of an idea of what that looks like. So if we took that first example, so we know we're already on the Sirius accelerator. We're in beamline 5 IBA, which is everything in this darker blue region here. We're on beamline 1, which is everything from the switch magnet all the way up to the chamber. And we've got beamline valve 1 and the status control for that actual beamline valve. So because I was pointing out a beamline valve, we've also got a ledger of all the various kinds of equipment and devices and we've got codes that we give each one of those, and we're trying to standardize what we're calling all those. Because we got the 2 new accelerators from NEC, we've tried to kind of mesh together the standards which they utilized and some of our existing ones to try to kind of make it as unified across the facilities as we can, particularly moving forward. I don't know if this is one of the biggest arguments your groups have, but we always get very upset about the color in which things are painted. And, you know, it's one of those kind of things we're trying to keep the facilities looking as consistent as possible so they present nicely. And painting was always an issue for us. So just a final brief thoughts. Like, having the guide has helped unify our group with a common language approaching the facilities. The document has actually undergoing its first revision, and it's benefiting from the wider input of the users of the document. So when we originally put it together, there was probably a few of the senior members of the group who we tried to kind of construct the bones of it and get the initial kind of vision written down. And particularly now it's being utilised. We've gotten a lot of feedback and a lot of input about how we might be able to kind of improve on it and add to it. So that's actually been quite a productive process for us moving into our revised version of this document now. And, you know, it is helping with sort of the facilitation of those discussions. And look, we likewise, with this conference alone, I think hopefully hearing everyone's thoughts and seeing the presentations about how everyone else is doing things as well, I'm hoping likewise through these kind of meetings we're getting a better, clearer language of how to kind of communicate better with you guys and interact more. So on that note, I'll thank you for that, and and hopefully we'd like to kind of hear everyone else's kind of opinions around this too.
Thanks, David. Yeah, we have 5 minutes for questions, or 3.
I had a comment. You mentioned the color scheme with the synchrotron. I don't even notice all the hutches are sort of that pale bluey green, and that's mandated, so we can tell contractors who come into the facility, whatever you do, do not drill into a pale bluey green wall, because that's for radiation safety means.
Oh, right.
Yeah, and so that's why they're all that color. And it's because some talk about doing a rainbow around the ring maybe at one point, but we didn't do that. We just picked on a color, not very exciting color, but that's the color. Do not drill into this, because that's what keeps the radiation in the hutch.
Oh, right. I think I saw you even had different colored racks and all kinds of things down there.
Daniel went for the rainbow colored racks on top of his. I don't think we have any guidance on colors otherwise. Well, I mean, there'll be things that for alarm colors got to be red and the like, but actual general furnishing or infrastructure colors, I don't think we have any firm rules.
Yeah, that reminds me. I think flashing lights cause problems for us as to what color a light should be. If something's okay, something's at fault, and something's all those kinds of things.
Yes, that's one that gets me too every now and then.
Yeah, our PSS system, red means it's dangerous, whereas on the EPIC system, red usually means it's not working. And so the hutch door being open is red in the PSS system, it's green in the PSS systems because it's safe for people or whatever. Whereas in the EPICS world, we say, oh, we can't operate. That's a fault. And there's a big warning on one of our screens that says the EPICS color scheme and the PSS color scheme is different.
And this sort of underlines the fact that different individuals have different ways of thinking about things.
Yes.
It depends on how you think about things, what a particular indicator might mean, and the idea that anything might be intuitively obvious is utter rubbish, because it depends very much on the observer. I'd like to raise a comment about unicorns as a kind of devil's advocate point of view. Unicorns are bad from many points of view, but they're also good in engaging people's interest. It's when the unicorn becomes an obsession that it becomes a problem, I suppose.
Yeah, I think you sort of made the comment somewhat. Probably it's more a problem about a herd of unicorns. It's where it sort of becomes a major issue, because there's definitely going to be places where you need a unique solution to a individual problem. Potentially, when you're looking at something like every beamline has a vacuum system, for example. Every high voltage deck has a cage and flashing lights and these kind of things, or every control screen has got some way of showing, a gate valve or something like that. Or even down to, I think Alan already mentioned about the motor controllers. I think they come up a few times. Not all of a sudden having a massive swarm of different controls that kind of support, so it can simplify the solutions that have to be put in place. Yeah, but I do certainly take your point that there's absolutely room in there for the occasional unicorn.
I think the thing is, depending on what sort of unicorn it is, whether it's something someone is really proud of and wants to talk about, you can get them to document it, and you can get them to deliver talks about it to try and disperse their knowledge, which is good. Or it's a sort of unicorn which probably needs a different motif, where it's almost a shameful thing. It's something that only one person can maintain, but it's not something they're particularly proud of. And getting that documented and talked about is harder, mainly because I think it's often a pile of tangled spaghetti that is hard to describe, and there's really only one person who's managed to get their head around it. The pile of spaghetti, maybe we need a different motif than unicorn for that one.
All right, thanks David for the talk. Next one up is by Navid. and he's going to talk about safety systems for human imaging.
Yes, thank you, Andreas and David, for organizing this. Good morning, everyone. I hope you have enjoyed the talks this morning. I am a senior controls engineer from PLC Group here in Australian Synchrotron. We take care of equipment protection systems and personal safety systems. Today, I'm going to talk about imaging humans in our IMBL beamline. First, I will give you a background about breast CT and what that is. So currently, health authorities recommend X-ray mammography to detect the breast cancer. But that method has relatively high rates of false negative and false positive diagnosis. And in contrast, 3D phase contrast X-ray CD offers reduction in physical discomfort of the patient and also reduced radiation dose. In that method, volunteers will lie on a bed on the PPS robot, the patient positioning system, and then will be imaged with a small amount of radiation that goes through the breast tissue. That PPS robot is actually a KUKA robot, and it has been modified for clinical applications. So to do human imaging in the IMBL beamline, we have modified the beamline. A new safety system will be added. A new clinical mode will be added to the beamline personal safety system, and also the robot will be modified both from hardware and software point of view. New programs will be added. Radiographer will have. I'm not going to talk about the robot itself. My focus is on the safety system today. So these are the beamline modifications. You can see the beamline here. We have added a new pink beam stop, which is almost the same as a photon shutter. We have added 2 new shutters and fast valves to stop the beam in a very short time. Test filters to calibrate the IPAS, a new imaging shutter. Of course, 4 ion chambers to measure the dose. We will have a new beam expander and a lot of changes down in hatch 3B. And also we have some 2 new beam detectors which are developed by Wollongong University. So these are the modifications in hatch 3B. A new access booth will be added to the hatch. Radiographer will stay inside the booth and run the scans. A new CT stage, we will have a new detector and all those modifications on the robot. So to design the safety system for those experiments, we decided that we need science requirements. We need to do a risk assessment, and in this case, we needed to come up with the experiment sequence because of the nature of those experiments. Risk assessment is the first and most important step in designing any safety system. We have used the ANSTO guidelines to do that. There are other equivalent methods that safety of machinery standards like ISO 12100 propose, but the process and the result is the same. You need to identify the risk, calculate the risk reduction factor, and then design your safety system based on other standards like IEC 62061 and ISO 13849. So you can see we have done that risk assessment for actually for most of the devices and components and different modes of the beamlines. You can see the risk assessment for the monochromator on this page, and definitely in some cases you need to have more than one mitigation to reduce the risk. experiment sequence. So we talked with the beamline scientists and identified 3 phases in each experiment. In first phase, IMBL staff will prepare the beamline for the experiment. In second phase, medical physicists will do the dosimetry and prepare the scan process for each patient. And in the third step, radiographer will do the scan. A flow chart has been developed for each phase, and it explains in details what should happen in each step, both from people point of view and also the safety and control systems point of view. So with all those informations of the safety system, the safety system must make sure that the beamline is set correctly for the experiment. It should stop the beam in a very short time if something goes wrong. It should make sure that the patients are safe on the robot. It should also control the experiment sequence and also coordinate many different systems like the beamline personal safety system, equipment protection system, the robot, and the imaging detector. So this diagram shows the relationships between those systems, and you can see that the core of that system is IPAS, and it actually has all those functions. We also have a new imaging detector, and we will need to modify the beamline equipment system, protection system, beamline personal safety system, and also the robot. So to design the IPAS, we need to know the required response time, the I/O requirements, the communications between different systems. We already talked about the safety requirements, and also we have some standardization requirements in the facility. To calculate the required response time, we know that the worst case scenario is when the monochromator is fully tuned, which gives us 40 milligray per second. Based on ANSTO guidelines, the target effective dose should be 0.24 millisievert. And based on that, the target mean glandular dose will be 4 milligray. And with those information, we calculated that the required response time for the IPAS should be less than 200 milliseconds. In that 200 milliseconds, these things will happen. The ion chambers will detect the fault, send it to the PLC. PLC will process that and send a command to close the shutter. There will be a delay and shutter will be closed, and then shutter will send the feedback to the IPAS. If at this point shutter is not closed and the beam detectors in 3B detect that there is beam, then IPAS will send a command to dump the stored beam. And after a delay, the beam will be dumped. We calculated and measured some of those delays, and based on those numbers, we realized that the PLC response time should be less than 50 milliseconds. I/O requirements, we developed a block diagram, and we can see that the I/Os are actually distributed in 3 different physical locations. We can see the number of I/Os and type of I/Os. We have some intermediate controllers and all sensors and actuators in the field. And we have different communication requirements for different systems. There is the internal IPAS communication. There will be a communication with EPICS, and also communication with different systems, the PPS robot, the beamline personal safety system, and the detector. And with all those information, this is the hardware architecture we have designed for IPAS. So we will have 3 CPUs in 3 different locations. We have used Siemens S71517F, and we will have a module to which is OPC UA capable for EPICS communication. We have used local modules for the PLC to improve the response time system that we have for the machine. We have used ultra-fast analog modules to measure the dose rate, and the most interesting part is that those 3 CPUs will be on a fiber ring to improve both the availability and the response time. And we actually used the Siemens software to estimate the response time, and based on the modules that we have selected and the CPU, it shows us that we can achieve 38 milliseconds for the response time. And the last slide, these are the next steps. We will build the hardware and develop the code for iPaaS. We will simulate it with the Siemens SIMIT software. Hardware will be installed. We will have an offline test and then online test without humans and the formal validation. Then we will do some online tests with humans, and then finally we will try to get the regulatory approvals. In Germany, we developed the robot programs. We will download them and do some modifications, and then do the offline tests. After that, we will test the of patients with the volunteers, and then modify the safety and again regulatory approvals. Thanks everyone. I'm happy to take any questions you have.
Thanks, Navid. We have probably time for 1, maximum 2 questions. All right, seems like you have explained everything perfectly. Well done. I'm sure if you have any questions, you can send Navid an email or catch him in the maybe in the breaks. Okay, next one up. I think you have frozen. Is Ishmael? Yep. Thank you.
Hello everyone. My name is Ismail Tabar, and I am in PLC group in controls team, and we look after EPS and PSS system. What I'm going to talk about today is sort of general information about our safety system and PLC-based safety system in the facility. So the base and core of our safety system is PLC safeties that we use for electrical and radiation safety interlocks in accelerator areas and beam lines. We have dedicated PSS for machine, accelerator, and individual beam lines. Existing PSS, I mean, should be say previously existing PSS system for the machine was based on Peel's PLC system, and it has reached end of life, and we had to upgrade the system. And also because we're going to expand the facility on the Bright Beamline projects, we had to add capabilities for new Bright Beamlines and also front-end PSS. Also, for the new beamlines, we had to develop a new platform. So all these sort of kind of led to an overhaul of safety PLC platform design, and that will bring state-of-the-art technology and benefits that we can get with it. So we looked at a few different platforms and decided to use Siemens integrated safety technology for both equipment protection and personal safety system. one of the most important decisions was to use an integrated system. So previously we had a separate platform based on a different PLC, Schneider premium PLCs for EPS, and a PLC platform-based PSS system. So we decided to go with integrated systems. Why we decided to go with integrated system? Obviously, it will allow us to have both system in one controller. We can basically save on cost of hardware, wiring, and also programming in one single platform, which is TIA Portal in this case. So within TIA Portal, we have fail-safe program blocks with password protection and CRC, change management, which is standard for safety system. As I said, obviously, it will reduce the PLC hardware and wiring costs. We can test systems without using the hardware, using the PLC simulation facility that is within the TIA Portal, and we'll talk about this a bit more. The platform that we use is based on ET200SP Profinet IO system, which is a flexible platform that we can scale and expand as we basically new requirement in future will be needed. All the safety hardware obviously is certified based on IEC 62061 to SEAL 3 and ISO 13849 to performance level PLE. So Machine PSS was basically our first project that we used the new platform. Basically, it has been done by a external contractor, but we were heavily involved in the process because we wanted to use that experience for our Beamline PSS. Machine PSS basically looks after safety interlocks, access control within the accelerator areas, which is storage ring and injection system. As I said, it was at end of the life, the existing system, and it was upgraded to a Siemens platform based on S7-1500 and ET200SP distributed I/O. And we added support for new bright beam lines and front-end requirement. It was a very sort of dedicated systematic cutover process under a tight timeline because we had to do it during the extended shutdown period of facility. That's why we had to test the PLC program before we started committing the change. This upgrade project completed very successfully with minimum issues during the cutover process. So this is a structural sort of diagram of the system. So we had two CPUs, one for storage ring, one for injection system. Each had its own dedicated Profinet IO network. And also CPUs needed to talk to each other because there are some inputs from one network that have some result that is on the other CPU. So based on that experience, we started developing Bright Beamlines EPS PSS based on Siemens technology, same platform as Machine PSS, but it is more an in-house development. We have EPS and PSS IO on the same node, so in that case it's a bit different because Machine PSS was only safety IO, but here we had equipment protection, which is standard IO, and also PSS IO. We have a Profinet IO network with media redundancy protocol that carries both standard Profinet data and also ProfiSafe, which is the safety data, basically. We have connection to EPICS which is based on OPC UA. So we decided to go with OPC UA. I'll explain more about OPC UA in the next slides. We don't have much time, so I have to go quickly through the slides. We also use CIMIT simulation platform for testing and simulating the system, and a comfort panel for visualization. So this is some pictures of the CPU cabinet and remote I/O cabinet that we built. And so let's talk about the simulation platform that we're going to use. So PLC Sim Advanced is a module within the TIA portal that is used for simulation of 7-1500 or ET200 SP CPUs. So basically what it does is we can manipulate the process image through either using APIs or using some external software. In this case, we're going to use CIMIT software. So CIMIT simulation software basically is used for virtual commissioning and operator training. It can be connected to either a real PLC or a simulated PLC. You can actually simulate the I/O that would be connected to a real PLC with CIMIT, and without having the I/O, you can start testing it. It has two modules, visualization modules that you can develop your screens that you use during the simulation, and a logic module that you can basically develop simulated plant behavior. For example, if you press one button, what happens in the plant? So this is not the PLC logic. This is the plant behavior, basically, if you need to simulate the plant behavior. I touched on OPC UA. So OPC UA will be our new standard to interface with EPIC. So before we had S7 driver to connect with S7 PLCs, or either Modbus TCP/IP, but we decided to go to OPC UA, which is Open Platform Communication Unified Architecture. It's a vendor independent and platform neutral protocol, and it has built-in security, so you don't need any extra hardware for that. You don't need basically very specific networking requirement, just simple Ethernet-based networking, and uses existing industrial Ethernet infrastructure that we have for EPS PSS system. And it has a high performance because of the fast communication features. OPC UA support has been developed within EPIC's community, so we already have our test system set up, and we tested with Siemens PLC, and it works well with within our test setup. In terms of CPUs, PLC side, there is an embedded OPC UA server on S7-1500 PLCs. So, and it's supported in TIA portal without programming. So basically what you do is just tick a box and your OPC UA server is up and running. The benefit of OPC UA, one of the most important one, is the symbolic addressing that allows adding data points to the interface with minimum effort. So as long as basically you have the same device name in PLC and EPIC side, adding a new device is as easy as just adding one entry in your substitution file in EPIC and one entry in your Siemens OPC UA data block within the PLC. A wide range of standard and user-defined data type can be used in OPC UA. Another important feature is you have timestamps. So basically all the data are timestamped, and you have the selection of either server timestamp or device timestamp. which means you can get fairly accurate timestamp resolution out of this system. So if you have multiple events happening kind of very quickly, you still can basically go through the timestamp data and see which one happened first. So fast scanning and publishing interval is available within 7 CPUs. So in 1517s, we can go down to 10 milliseconds, which is basically within a PLC cycle. So if you have 2 events that happens in consecutive PLC cycle, you will see them as separate entities in your OPCA in terms of timestamp. Data exchange is available either via pooling or subscription. So you can either keep sort of reading data from the interface for specific devices, or you can subscribe to a specific tag, and then the OPC UA server will send an update to the IOC when the tag has changed. So that's it, basically. If you have any question, please fire away.
Thanks, Ismail. Maybe one quick question. If anyone has it? Oh, sorry, if anyone else has it, I don't have a question. So.
Okay, yeah, fine.
No? Okay. Well, thank you.
No worries.
Okay, so next one up is me. Can you stop sharing, please, so that I can start?
Yes, I'm looking just for.
There we go. I'll stop it for you.
Yeah, can't find it. Windows gone. Okay. Yeah.
Okay. So I'm going to be talking about the platform management that we do at the Australia Synchrotron. I am a part of a team that's called Accelerator Controls and Support Systems. So that basically means that while we support the accelerator from the controls point of view, we also provide some support for the rest of our group. So one of the things we provide is a platform management process in hope that we make life easier for the other controls engineers. Good job. So for the platform management, we were thinking in terms of mission. It's basically, it was a combination of having things done quickly and easily, and also standardizing on a few things while we're doing it. So here's a short list of what we basically wanted to achieve, and how we wanted to achieve it was to basically just to develop a few tools that will streamline the entire process. And while we're doing that, we were thinking if we're doing it, we might as well try and do it relatively quickly. I mean, the entire process to be relatively quick, and then end up with something that's standardized so that everybody can work on, and so that everything has the same look and feel. So you can have engineers going from Beamline to Beamline and not be lost on different hosts. Okay, so quick look at the quick host setup. This is kind of an overview of steps that are required to set up the host. So we start with really the fastest route is creating a VM, a virtual machine. But if you have to have a physical host, that's fine. You just have to take a few extra steps. But in general, you create either a virtual machine or a physical host. You set up the physical host in the lab somewhere. If this is the virtual machine, you have an option of choosing a few different templates and then basically running a single script to finalize everything, and you're good to go. If this is a host, a physical host, then you have to do a bit more because we can't really have templates for physical stuff. So you have to install the OS and run a command that installs a lot of software, but it doesn't require a lot of input, but it takes a bit longer. So looking a bit more in detail, at the first step for the virtual machines, like I said, we have two different templates ready. One is basically just a hardware configuration for a virtual machine. And you get nothing. It's just a VM without an OS, without anything. This is kind of useful if you want to have something that's not standard. But I think nowadays people are mainly using the other one, which is a pre-built template. So pre-built in this case means that this is basically a snapshot of a virtual machine that's had most of the stuff already installed on it, and that snapshot is then converted into a template. So whoever is then creating a new instance from that template basically starts with a lot of stuff that's already there, and it's just a matter of finalizing it for that particular machine. If you have a physical host, you need to connect it somehow. So yeah, we can't do that for you. We don't have a standard workspace to set this up, unfortunately. Maybe we should, but you need to get it onto the network, find a screen, keyboards, whatever you need to get it going. So in case of then the physical host or a virtual machine that's using only the hardware configuration template, you have to install the operating system and software and everything else, the configuration and stuff like that. So we've kind of streamlined that to an extent. So if you have the VM, you need to clone the template. Takes about 6 minutes usually, and then you run a kickstart. So this is a process that installs operating system and sets up some like YAML repositories and just some basic stuff. So the second step is the same on the physical host as well as on the VM. And once that's done, you run a script that installs everything for you. So we're not using, I think Nick said they're using, was it Nick? They're using Puppet. I've seen people using Ansible and stuff. So we're using Salt. It's basically just another software that does configuration management for you. So basically we do that. But we don't push it from the server, but we do it the other way around. So the clients request the configuration to be set up on them. So this takes like 38 minutes, so it's not great, but I think compared to doing everything manually, it's still decent. The next, however, if you go with the pre-built VM, which has most of the things installed, really all you have to do once you clone it is run one script to install the stuff that's bespoke for that machine. So set up host names and stuff like that. So basically, once you're in, you clone it. Once you're in, you can see here on top, you just run the finalized build. And that's done in 13 seconds, in this case. And you're done. So the summary of this step is basically you go in 6 minutes and a half, you go from 0 to hero, which I think is pretty decent. Okay, and the last step is where the two branches join back in, is a bit of housekeeping that everybody has to do manually. So set up new passwords. Hopefully we have no process on to force people to set up new passwords, but we encourage them to. Set up, we like to see some message of the day on Linux hosts, just to know what's going on that particular host. There's also a script, like Andy mentioned before, to pull all of the pre-built Epix modules that are hosted on the on the storage network to pull it locally, because this way, if the network goes down, you can still keep on going. And after that, you're pretty much done. So what you get with this process is a lot of things set up for you in terms of configuration. So like NTP-NFS, RFS stuff. So you're mounting everything users created and their default password set. We install VM tools if that's a VM, so they can monitor it. We get the latest versions of Python, or the one that's currently the standard for us. Yeah, I don't know. There's a bit. So we do LDAP notification, Zabbix, so that we get notifications if something's wrong with that particular host, if it's losing too much like memory or something, or if it restarts. You can subscribe to emails to be notified for that. Some development tools, some cron jobs that do automatically back up autosave files and support our archiving paradigm, and just some random packages that are just generally useful. You also get a standard directory structure, so standard autosave folder, like config files, and so these are like support scripts to run services. So this is expected to be on every host and always in the same place, so you know where to look if you want to find something. And also you by default you get a status IOC for that host, which doesn't do all that much other than monitor the host itself. So in terms of load and CPU used and memory, if you can access the network or if that's an issue. So that comes for free. So with that, if we look back at the mission, we kind of cover, I think, most of it or everything. So we get an operating system which is standard. We currently support CentOS 7 and CentOS 8. We decided not to support CentOS 6 anymore because it's officially not supported anymore, and it's a security risk. You get some software packages installed. You get consistent naming conventions when it comes to setting up a host name, because we can enforce some rules. So when you run the script to set up the host name, we can say, no, that's not good. You have to pick something else. Directory structure, like I said before, we do some backups, and we do a bit of diagnostics with Zabbix, as well as with the status IOC that you get on each host. And I think that's it. But room for improvement or moving forward, yeah, Docker. A lot of people are talking about Dockers, and the CI/CD. Anyway, continuous development and deployment and improvement, and yeah, so we'll be looking in that space. Any questions?
Not so much a question, unless someone's got a question.
I was going to say I have a comment rather than a question.
Okay.
And my comment is that along with things like the pre-compiled bundle and so on, it's this sort of initiative that has made my life a bit of a joy working at the synchrotron. There's the fact that I don't have to spend days and days and days getting a new computer host going. It's not quite as easy as your slides make it look, but it's a damn good start, because, you know, like you said, within half an hour I have a host, I have an operating system, I have most of what I need. I spend the next few days sort of tinkering and customizing it to get it to be exactly what I need, but you know, it's a huge advantage. I think the disadvantage, another comment of this sort of system is it's not as easy to upgrade as it ought to be. And the result of that is that you end up with a sort of trail of heritage machines where you're afraid to change them in case they don't work anymore, and the tail goes on, and you've got newer and newer and better hosts, and hopefully eventually the old archaic ones just die off and don't get replaced with new ones. But upgrading them, it might just be me, but I'm a little bit afraid to upgrade things that have been created this way.
Okay, I think we thought about this, and a lot of people go down the route of having this managed centrally. So we could have a salt server or salt master pushing out updates. So if you change the process, if you change what's installed or what versions are installed, you just push everything on all of the minions. It's what they're called. But I think, I mean, from talking to people, they weren't too keen on that. So just generally controls people on Beamlines. They want to be in control of what's going on with their host, which makes sense. So we're not doing that centrally. And in terms of being afraid to update, I don't think you should be. But I understand why you would be, because if something comes as a black box and just installed for you, and you're not entirely sure how it's been done or where it is, then yeah.
Question for Terry: were you talking about OS upgrades or bundle upgrades in that context, or both?
Both. And often it's not so much a personal fear or fear of the person who's responsible for doing it. It's often the scientists who rely on this thing saying, "Don't touch it; it works."
Yeah.
That's a tricky one. I think certainly with the bundles, I try to get them out before the shutdowns. There's a long time to, a reasonable length of time to upgrade to the bundle and try it out.
Yeah.
And I suppose if the bundle upgrade doesn't work, you can always roll back to the previous bundle. Or if it's a virtual machine, you can create a new virtual machine on the new bundle and try it. And if it doesn't work, you can run up the old machine again.
I suppose in terms of the actual host, rather, so forget about the bundle for the moment, which is a similar but different arrangement. It's a little bit of extra work that you have to do to make a new host usable in the context where, things like Kickstart haven't quite covered what you need. If there were an easy way of capturing those extra customizations, which are almost inevitable, so that you could reapply them quickly. There probably is. I just don't know it.
Yeah, and certainly I had to set up a couple of physical boxes recently, and unfortunately the Kickstart didn't do what I wanted to do. But one tip, certainly on a physical box, I take a snapshot of the root bash history. After a week, there's 1,000 commands or whatever I've put in there, and okay, it's not a great way, and you have to dig through it. But if you can't quite remember what you did, you can certainly look through it and say, "Oh yes, I had to install that special package, or I had to create this folder, or whatever." But
that's a good suggestion. I must keep that one in mind.
So, Andreas, do you want to ask a couple of quick questions too? So, when you deploy those first systems, do they just sort of go to some kind of neutral zone for testing those out before you put them into production?
Well, yeah. So there is a process that people should follow, but I'm not sure if they do follow it. We have a physical thing called an integration lab, and we also have a network that's assigned to that. But it's also available in our VM stack, so they should create everything on the integration network. And we put everything, if it's a virtual machine, they should create it in our, like a test repository of virtual machines. So in that way, it's separated, it has separate resources. So if something goes wrong, it's not eating away from the production stuff. So everything should be developed there, it should be tested there. And then once they're happy with it and they know it's working fine, you move it to production, and you have to go through a checklist, that everything's set correctly, that it doesn't have, 64 gigs of memory assigned, and just basic, housekeeping stuff ready.
So I guess the other side of this was, since you've made the process of producing the hosts much easier and quicker, has that led to people producing more systems all over the place, or is it sort of kept the numbers to what they would have been beforehand?
I think it really depends. Some beamlines, I think the hosts on some beamlines have exploded a bit. I've also noticed that people would create hosts just to test something.
Right.
You know, so almost like you have 5 development hosts.
Yeah. One thing it has led to is the use of multiple hosts versus multiple epics IOCs on a particular host, for example.
Yeah, you can do that. Sorry guys, I'm gonna have to stop here because Nick's waiting to give us his presentation at the last one before the lunch break. Thank you, Nick, for this agreeing to talk about the ANSTO security risk management.
Hello, hello. I've only met a few of the audience in here, only a few names that that I recognise. Thanks for the invite here. I've got about 10-15 minutes of content to go through ANSTO's cybersecurity risk management here, and I know I'm before lunch, so I'll be as quick as I can. Jump in with questions, or is there a raise hand in Zoom? I don't use Zoom too much. Whatever, jump in with questions, raise hand if you want, or save it to the end. Let me just share screen. Great, okay. So ANSTO cybersecurity risk management, and there's a little bit of tailoring of this one for accelerator engineers for the audience here. This is some common material that that I've been shopping around to a few different areas inside and outside of ANSTO, just explaining sort of what we're doing and what the context is here for our cybersecurity risk management. The first bunch of slides are going to be kind of generic and a bit more nuclear security focused to give the context and a bit of the prioritization of what we're doing and what we have been doing over the last year or so while I've been in this role. So what is this? This is how the nuclear industry thinks about cybersecurity risk management, and I hope all of our accelerator people out here don't really have a nuclear security aspect to what they're doing. If you do, please let me know, because that's very interesting to me. But it's also talking about the standards that we're following, and then how that kind of flows down to the work that that you're all doing and that we're doing across the organization, whether that's in science or in manufacturing or nuclear operations and so on. So what isn't this? This isn't a technical cybersecurity, hacking, compromise, vulnerability type talk. There's a little bit of it at the end that I'll get to. But if you're expecting like this is how to red team things and so on, it's not going to be very heavy on the technicalities just yet. But I'm super keen to do more of the detail work with you all in the next 6 months or so as we actually start to pull the levers on our cybersecurity maturity improvements. So strap yourselves in. I'm going to start off by who am I? I'm not going to talk about what is ANSTO, because we all know what ANSTO is, I hope. And then a bit of context around ANSTO's computer systems landscape. What is nuclear security regime? What do our regulators have to do with it? And then how do we then translate our national and international guidance into standards and practices and processes for people to then implement? And how do we integrate that with our asset management planning? And I don't know how well the accelerator world across ANSTO is on top of their asset management. I know there are areas of ANSTO that are really bad at their asset management. And so I just want to talk about that a little bit. And then the main event at the end is the ANSTO Cybersecurity Risk Management Plan. This is a documented plan that will apply across ANSTO. And this will tell you, I hope, and if it doesn't, we need to make it. It will tell you these are the cybersecurity things, whether that is technical or organizational or some other capability that you need to have in place on your computer-based systems. So I hope that's the answer for the questions that that the audience here is looking for. And if it's not, let me know and we can keep going. So very briefly, who am I? I'm Nick Howarth. I'm the Cybersecurity and Operational Technology Manager at ANSTO here. I've been with ANSTO for just over 10 years, got my long service leave ticked over last month, which is great. That was all supposed to be burned across holidays this year, and that obviously hasn't happened. So sad times. Most of my time at ANSTO, I've been the IT OT system engineer at Opal. I think that's kind of equivalent to like your platform engineer type thing. I was responsible for the computer and network hardware, operating systems, virtualization, security, and other things like that as a platform for our instrumentation and control engineers to then use to run and maintain Opal. If you haven't had a tour of Opal and you want one, let me know. More than happy to show you around. It's a beautiful machine. Now I'm the cyber and OT manager for everything at ANSTO. And I've been in that role for about 12 months. Historically, we have not had good resourcing and good capability in this space. My predecessor was by himself for a lot of his time. I now have a team of me. I have 3 cyber people and I have 2 OT people, and we're bringing a few more in as well. There's a lot of work going on in the radiopharmaceutical space, manufacturing space, so lots of things happening. So ANSTO's computer-based systems, basically anything that's running software. This is not just a computer or a server. This is embedded devices, PLCs, other IoT things, cloud computing, fog computing, if you want to be that hipster. But really anything that runs software is going to have, and has, is connected to a network, is going to have some kind of cyber footprint, some kind of cyber security vulnerability exposure or something like that. And some of those pose very significant risks to ANSTO, and some of those really don't. And so how we perform that risk assessment, that risk management, and how we prioritize the work that we're doing in the cybersecurity space is what my job is. So you probably know ANSTO has a very unique and diverse set of computing technology, computer-based systems, and accelerators are a big part of that. And so early on in my time in this role, we put together this very high-level computer-based systems or technology landscape across ANSTO. And for those in the audience, the accelerator side kind of sits over here, synchrotron, CAS, and so on, and other beamlines and other landmark infrastructure and scientific bits and bobs. And we see that from a risk perspective as kind of its own thing, kind of distinct from our regular corporate computing environment. So that's SAP and all of our other software systems and services and so on, and your regular ANSTO endpoint, desktop, laptop, whatever. And then the risk profile there is then different from our OT or radiopharmaceutical or radiological or nuclear related computer-based systems on this side. So physical protection system, Opal, A&M and Building 23 for health. And the very simple example I like to use is the systems that we have in health, in ANSTO Health for radiopharmaceutical manufacturing. We don't want those to be changed, right? There's a lot of quality assurance that goes on, good manufacturing practice, and we want those systems to be very deterministic in their operation. We want to have a very high level of assurance that they're doing what they're doing, because fundamentally they're making medicine that gets injected into people. And if they are compromised or disrupted in some way, that affects the supply chain for Australia. And we saw that last week, not with a cyber incident, but with a blown light bulb in a hot cell, ends up delaying manufacturing or postponing manufacturing for about a week. And that equates to a couple of thousand patients ended up being disrupted and so on. So bad outcomes in there from very small incidents. Compare that to the scientific side of the world, the accelerator side of the world. If a beamline goes down somewhere, if an accelerator goes down somewhere, it's a big deal. Yes, you have teams of people around there supporting that, and you might inconvenience some scientists and disrupt a little bit of research. But that doesn't make front page stories, doesn't make front page of the internet or in media outside. And so that risk profile is quite different. Fundamental to that, we don't want to apply the same level of control that we have or that we need to apply on the radiopharmaceutical side of the world or the nuclear side of the world than we want to on the scientific side of the world. And so that's kind of acknowledged at the very beginning, this kind of graded approach, defense in depth, commensurate to risk. So I just want to kind of contextualize the rest of this talk to say that we kind of understand that, and maybe we need to know some more detail of that. But we in no way expect that we will lock down and secure everything on the scientific side as much as we do on the pharmaceutical side. So very briefly, the nuclear security regime, if you're not aware, ANSTO has obligations under, or the Australian government as a sovereign state, has obligations under the Non-Proliferation Treaty. and related instruments and treaties and other things to protect nuclear material. This is nuclear security. This is safeguards. This is making sure that nuclear material that the state has, and the operators within that state and the regulators and so on that are enforcing this, they have obligations to protect that nuclear material, to make sure it doesn't go where it shouldn't go, and it's not used for purposes that it shouldn't be used for. And this is all through the IAEA and a range of treaties and other instruments like that. So that gives us then 3 priorities for nuclear security. I'll touch on them very briefly. The first one is physical protection. So for ANSTO, that's Lucas Heights, and that is gates and fences and cameras and motion detectors and so on. And you think about these systems that we have for physical protection, they're run by computers. The next nuclear security function is nuclear material accounting. So effectively a database of where is our material and where has it been, and keeping track of that. Quite small, quite simple, quite straightforward. And then the last one, nuclear safety. And for ANSTO, that is basically a protection system one of the protection systems we have at Opal. It is a digital system, and does have an pretty interesting and significant cybersecurity vulnerability that I can talk about. Ask me a question about that sometime. So, question I pose to the audience, or maybe a bit rhetorical here, what are your sensitive functions in your systems? Do you have safety functions? Maybe it's not nuclear safety, maybe it's radiological safety, maybe it's other workplace health and safety type functions. What are they? Are they appropriately characterized? Are they appropriately controlled? And are you confident in that? Do you need help in that space? Do you have intellectual property concerns? And I know the response I get from a lot of the scientific community is, I don't really care. It's data, and it's either not contextualized and not valuable, or even if it is contextualized, it's open research anyway. So from an IP perspective, what are your considerations there? And then physical security concerns as well. What is your overlap with physical security and cybersecurity? So going back to ANSTO, the 3 important nuclear security things we care about is physical protection, and then Opal, and then NMAC, and they all have a cyber footprint. And so that's where we put the most control. And I hope you appreciate, the most control is on this side and your accelerator on that side. So that kind of says the level of control and level of risk that we're managing. So where do our regulators fit in? ANSTO has lots of regulators. We have ASNO, who we can basically say are our security and safeguards regulator. We have ARPANSA, who is our radiation protection and safety regulator. And then we have Department of Health, the TGA, and the FDA in the US. They audit us and issue us licenses and permits and so on from the pharmaceutical manufacturing side of the world. So computer systems validation and that side of things. ASNO give us a permit, and the permit gives us very clear cybersecurity, very clear security requirements, of which there is a cyber component to that. ARPANSA gives us licenses for our different facilities where there are radiological safety concerns or issues, and ARPANSA give us requirements under licenses that we have to fulfill. And then we have primarily GMP, good manufacturing practice requirements coming from our pharmaceutical regulators. So all of these come together and give us an idea of what are the operational and physical security and quality requirements we have, and cybersecurity is part of that as well. So we have to manage cybersecurity risk like we would manage those other risks as well. So in practice, what does that mean? And now we're sort of getting to the point where, what does this mean for you? What does this mean for our accelerator community, the broader scientific community, and ANSTO as a whole? So in practice, what it means is we take the Australian Government Information Security Manual, the ISM, and we take guidance from the IAEA, NST 47. That number will change in the next year if you're keeping tabs on that. But we take these 2 guidance documents, we mash them together, and that gives us our cybersecurity risk management program. So NST 47 is here, it's published by the IAEA. It's technically still in draft, but the IAEA and we are training people to it. So I'm considering it as good as published. And it talks about what are your facility functions and assets with a skew to nuclear security. What is your design basis threat? So there are threat actors, malicious actors out in the world, or maybe inside of ANSTO. Who are they? What are their capabilities? What is that level of threat that is expected or required that we must defend against. The attack trees are then is how are those threat actors, what is the postulated methods that they could use to attack our systems and achieve their objectives. And then from that, we need to design a defensible security architecture, which includes cybersecurity levels and zones, which I'll talk about in some detail shortly. And then within those levels and zones, apply controls. So the ASD published the Australian Government Information Security Manual. It's available online, cyber.gov.au. Hit the government button there and you can read through that. It is long. It is a big list of controls. And it basically says you need to have some governance structure in place. You need to do some kind of risk assessment, and then you need to select these controls to apply to those systems. So that's what we kind of do. Bearing in mind that the ISM is very information security focused, and ANSTO does not have just information security risks. We are not like most other government departments, government agencies. We're not just IT, information technology. We're also physical assets and other physical things that have computer-based systems running them. So nuclear reactor, accelerators, beamlines, and so on. So we need to take this in the context of not just information security, but in broader cybersecurity and so on. So what does that mean? We do our risk management and our architecture piece following IAEA guidance, and then control selection comes from the ISM. So both of these are publicly accessible and consumable and readable. They are long and a bit dry, but then it's my job and my team's job to roll this out with everybody across ANSTO. And hopefully that results in some nice, safe, secure and sustainable outcomes for everybody, commensurate to risk. So we've already said this is our nuclear security focus here. Good. What is our design basis threat? I won't go into a lot of detail to this, but I will say that it is an unclassified version is published and publicly available, and mostly focuses on or is directed against, directed to systems that are involved in the protection or use of nuclear material and nuclear facilities. So great news for you guys. Doesn't really apply to you. Cool. Means the threat level that we establish for our nuclear safety and nuclear security significant assets is high, but because accelerators don't have nuclear material, the threat basis we will risk assess to be lower than that. So it's great that our threat model is given to us by our regulator. It means we have to make less assumptions in that space, and it's easier to validate work that we're doing and assumptions we're making. But a question here then is, okay, if threat basis is given this high, what happens if there is a beyond design basis type of cyber attack? What does that mean? And that means particular things in the physical security side of the world, but this is a question that's kind of hanging open in the cyber side of the world, which we're working through. So we know our threat level, or we define a threat level. From that, we then define what are the attack trees, what are the techniques, tactics, and procedures and so on that a threat actor would follow commensurate to that threat level to meet or to reach their objective. So what do they want to do? They may have an objective of stealing information. They may have an objective of disrupting operations, destroying equipment, whether that's destroying data or physically destroying plant. But how would they achieve that? We have to think like the attacker, and how would they then carry out some attack and achieve that objective? So from those attack trees, if we go back, if we think these are all the different things they could do here and there, what are the controls that we will then need to prevent or detect or respond to that element of the attack tree? So this is where we define our defensible security architecture. There's many to choose from, but we basically say defense in depth because it's a hybrid of all of it. And within that defensive in depth architecture, we then pick the controls that we need to mitigate those different parts of the attack tree we've set before. So defensible security architecture means we identify those systems that are most risky, most important to us, and require the highest level of control. And we have some graded approach to say more controls where we need them, less controls where we don't need them. And that looks like this concept of cybersecurity levels and zones. It basically means highest risk in here is the lowest number of assets, is the lowest number of functions, the highest significance in terms of risk. And with it being a smaller number of assets, applying more risks, more controls to a smaller number of assets, it balances out that way. What it also means then is if we can break up our systems into zones, whether that be a physical zone, a network zone, or something like that, as a way to segregate and control communication and connectivity between those zones. That's the principle of zoning. And then levels is an abstract concept to define a level of cybersecurity controls applied to assets within the zones within that level, if that all makes sense. What does it mean in practice? So we define our cybersecurity controls within the levels appropriate to the attack tree, as I've said. And in practice, it basically means fundamentally everybody needs the essential 8. And these are 8 controls that come from the ISM. And they should be applied basically universally to all computers. And then we bolt on additional controls on top of that, commensurate to risk. So we've defined our controls for our assets. Now they need to be implemented and maintained. And this is then where we talk about integration with asset management and the concept of cyber-informed engineering. This is where we understand what are the controls that we need, what are the organizational capabilities and organizational structures and resources and so on that we need to be able to first implement those controls, but then maintain them for the life of that system. So if we have a reactor that has a design life of 50 years, if we have an accelerator that has an operational life or design life of many decades, we need to ensure that we are not only building these cybersecurity controls in at the beginning, but then building in the capabilities and the resources in their asset management plan or strategy to then maintain those controls and evolve those controls over time. In summary, that basically means you need to be upgrading your stuff all the time, and you need to keep upgrading it, whether that's hardware or software or whatever. That has to be an assumed asset management function that is always being performed. Comments from the last talk from Terry around, we've built a server and it's been tweaked and configured and so on, ready for use. But then it's hard to touch that and upgrade that, when you have to. My kind of point to that is you should always be touching them and always be upgrading them and maintaining that capability to touch them and upgrade them and maintain them as an operational sort of priority. ANSTO has a huge legacy, not just in accelerators or wherever, but around all of ANSTO has a huge legacy issue of old unmaintained computers. And that's purely because everyone's afraid to touch them because they haven't been touching them. And if you stop touching them, then you're afraid to touch them. So yeah, integration with asset management then. Cybersecurity requirements fundamentally need to be treated the same as safety or physical security, functional requirements, environmental requirements, or whatever. They need to be built in as early in the procurement design process as we can. And they need to be baked into your overall asset management, your strategy, planning, and the practice. So this is an asset management gap we have across ANSTO, and I think just based on the audience size here, I think this is less of a problem in the accelerator space. I think you've got a lot of people and a lot of capability, and this is also why I haven't really spoken to a lot of you in depth about this yet, because we've been busy focusing on the other side of the world where we don't have this capability and so on. But it's this asset management gap of who is responsible for doing this work and has the resources to do them and the right capabilities to achieve this. So this is a bit of a summary of computer security for nuclear facilities piece. Just from a risk assessment piece, what are your sensitive functions and assets? Can you have safety, physical security, quality, or other objectives like that without cybersecurity? We follow IAEA guidance and ISM. What is your threat basis? And that's where I'll come in and help you with that as well. But make sure that this is all baked in fundamentally to your asset management. So the technical bits at the end, which I hope you've all been waiting for and are super keen to see. What does it mean for accelerator engineers? So if you're not familiar already, there's an initiative that's going on through a variety of projects and operational work that IT are doing and the NSTLI side of the world are doing around ScienceNet. Being able to better integrate and share resources across the scientific infrastructure. And part of that is going to be establishing good standards for that infrastructure, operating systems, networks, cybersecurity controls, identity management, etc., etc. They really need to be designed and architected upfront, and some good decisions made for those kind of core, fundamental components. And on top of that, we can then build good technology on top of that. So we all need good asset management practice in place to have any chance of having good cybersecurity risk management. So key example here, and this isn't to throw shade on anyone, but one of the accelerators somewhere has a Windows 98 machine that's very important to its operation, apparently. I haven't seen it myself in person. And no prizes for guessing when a Windows 98 computer would have been procured and installed. That's a long time ago, and no prizes for guessing how long Windows 98 has been out of support and what kind of vulnerability footprint it then leaves to us. So that's an example there of very poor historical asset management, right? This concept of we have designed a computer and installed it and it's working, it's performing its function, and we'll never touch it again. That is a terrible, terrible way to do things nowadays. If you're afraid of touching things, if you are not maintaining things, not patching things, not replacing them at end of life, you are leaving a huge vulnerability exposure, cybersecurity vulnerability exposure to ANSTO. So the ScienceNet piece here around separating out scientific infrastructure, segregating that from the rest of the corporate network or other networks is part of mitigating that. But fundamentally, it requires better asset management to actually resolve. The last piece I'll leave you with, and I have a little preview for you, is that the ANSTO Cybersecurity Risk Management Plan, this is a document that will be published in the ITBMS formally. It should tell you exactly what organizational, procedural, and technical controls that you need to implement and maintain across the facilities and assets that you're responsible for managing. And the cybersecurity team is here to help you do that, whether that's by providing some amount of service and support centrally, or giving you good guidance, good practice, and helping you build capability locally. That's the purpose of the cybersecurity team. And I do have a very quick preview for it here. So this is the draft document. It's so draft it doesn't even have a number yet. It is a bit long. This is the meatiest part of our cybersecurity management framework. And I'm also looking at a track changes version. If I go no markup, that's better. So the key point here is we talk about everything I've said in this presentation. There is assets. Why are we doing this? What are the outcomes? How do you use this document? Classification from an InfoSec perspective. We call out our nuclear security functions, our design basis threat we talk about, talking about some recent examples. Here's our very high level attack tree. Here is our defensible architecture. Here is our security levels straight from NST 47. And then here are the controls that everybody needs. The common controls for everything are listed out here, and I'm not going to go through them all in detail, but the idea here is that the asset managers for our different facilities across site should be able to read this and say, good, my facility, my asset needs to have this, and needs to have this, and needs to have this, dependent on what level or what zone that it's in. So that's common controls. Level 1 systems, this is Opal, this is the physical protection system. It needs dedicated physical architecture, physical isolation, high level of configuration management, documents, drawings, all this really good hardcore stuff. That's not what we need for our accelerators, right? So this is kind of where we now see the graded approach, right? So level 1, hardcore nuclear security things, not really relevant for accelerators, that's good. Level 2, radiopharmaceutical manufacturing, right? So not as hardcore as a reactor, but still, still pretty risky. Still needs a good level of control. So it needs a few other things. And then level 3, this is our corporate computing side of the world. And so this is where we have our essential 8. So application control, application patching, right? Are we patching security vulnerabilities at an extreme risk that are assessed at an extreme risk? Are we patching them within 48 hours? The key point here is extreme risk. What does that mean? We can answer that one. Macro controls probably don't apply because you don't have Office on your machines. That's good. Application hardening. Again, this is more a web browser thing. If you're not capable of browsing the web and don't have web browsers on your machines, great. You've already satisfied that one. Administrative privilege controls. Part of that's changing good passwords and having good idea of who's got root accounts or other privileged access. Operating system patching, again, if they're extreme risk, they need to be patched in 48 hours. So the key point there is what is extreme risk, and do you have the capability to turn it around in 48 hours? Multi-factor auth for remote or privileged access, and then daily backups. So if there is some event, you can restore from it. A whole range of other controls at this level as well. And the last piece I'll leave you with then is cybersecurity level 4. And this is where we think the scientific infrastructure fits, whether that's synchrotron, CAS, ACNS, and the other platforms around there. And the answer that we have here for level 4 is that it's basically level 3, but we anticipate a lower level of maturity. And I don't have a solid answer for what that means yet. And this is a process that we need to go through together and with the other scientific facilities as well to answer this. And this is where I come in and where my team comes in to go through this process. At the end of this, though, I hope that this document is a very easy, transparent, simple tool that you can all use to answer that question of what do we need to do? How do we do it? What resources and so on do we need? So I think that's it from me. Thank you very much. Happy to take questions either now, or if you want to go off to lunch, do it and hit me up on email or some other medium.
Thanks, Nick. So unfortunately, the thing that I got from this, because this is the most applicable to what I do, is that we can use you as an excuse to force our scientists or to explain to our scientists why we need to touch the host, even if they don't want us to.
Yes.
That's good. So and if they don't like it, we'll give them your phone number.
So from a leadership organizational kind of perspective, right? Cybersecurity should be here as an enabler, and we should be supporting and enabling the business to do the things, and security is a risk management thing, and it's all about that kind of perspective, right? I try and be as much of that kind of person as I can, and that kind of function to play in the organization. But fundamentally, if there is a risk that is unacceptable to ANSTO, and this is kind of described in ANSTO's risk management framework and appetite and so on, if there is a risk that is unacceptable to ANSTO and we can clearly articulate that, I'm more than happy to play the bad cop and say, no, you can't do it that way, or we have to do this. I don't like saying no. I try to be more, actually, we can do it this way instead, or maybe we can do something differently. But if it is unacceptable, I'm more than happy to say no.
Okay.
I think make an observation. I think it's great to have, or it would be great to have, a list of easily identifiable targets for cybersecurity. Yeah. What would be missing then, of course, would be how do you do it?
Yep.
And the questions that get asked around in that realm are, well, we've got this Windows 95 box on our beamline because when we bought this piece of hardware or something, this was the only thing that the vendor supplied and supported. There is no substitute for it. How do we fix that problem?
Yep.
That's the sort of question that would be asked. And that runs through a whole spectrum. It's like, okay, the cybersecurity rules mandate that we must lock down all our ports, firewall protection. But if we do that, then this service breaks, The Epic's control system breaks because it requires certain ports to be open. It becomes a bit of a tangled nightmare to try and say, how do you conform to this cybersecurity requirement?
Yeah.
And unless we have experts answering that question and probably a team of experts answering those questions on a regular basis, it's very hard to reach those targets. The other observation I would make about you must patch and upgrade and update and so on your operating systems and or other bits of software. Again, if you leave a human in the loop to make those decisions, then it won't happen. The only way to...
I disagree, Terry.
Yeah, I know, but let me finish and then we can have a discussion about why. The only way, in my opinion, to make this happen is to make it automated. And that means also, of course, an almost automated method of rolling back out of it?
I'll answer that first. That test patching automated thing, I'll talk to that first, and then I'll talk about the expert piece as well. My perspective on the automation of patching and so on, yes, not to the exclusion of having informed expertise and subject matter experts or whatever in that area. But yes, the more you can automate, the more you can centralize that kind of activity, the better it is, right? In my opinion, patching of applications, patching of operating systems is a core, like, routine function, and it is a core operational function, right? You have to have that as routine, as automated, as scaled out as you can. But to enable that, to facilitate that, it goes beyond just patching things, right? In the Windows world, you have a WSUS server that pushes out patches to Windows endpoints. And maybe you've got like a tool like SCCM or something doing applications as well, or maybe the apps are packaging themselves, whatever it is. And in the Linux world, you've got a variety of tools, whether it's Salt or Puppet or whatever else that can help in that way as well. That's one part of it. The other part of it is to really operationalize patching. It's also really operationalizing testing, right? When you deploy a patch somewhere, you might break something, right? It's a lot better today than it was 5 years ago or 10 years ago, but you still have a risk of breaking something. So how do you have an assurance, and how do you have some automated assurance at scale that when you are patching things, that you're not breaking things as well, right? And in the industrial control system side of the world, that's really hard to do because a lot of the technology out there is proprietary and don't have tools and APIs and other facilities and things you can use to automate your testing at that kind of scale. I don't know what it's like for Epics and the accelerator side of the world. I'm just not familiar enough with the technology. But to me, what comes hand in hand with being able to operationalize patching is operationalize testing of that as well. And it should be something that you're doing continuously. Your comment there around you need expertise, that's exactly it. If you don't have a defined person, a defined responsibility, that you are responsible for ensuring that systems are patched, that security controls are implemented and maintained, and there's measures to that and metrics to that, it does require expertise, right? When I started at Opal, this is 10 years ago, there was not a person in reactor operations. There was not a person that had the technical capability, knowledge, awareness, connectivity with others, with peers or internal or external. There was not a person who was looking at and responsible for the reliability and security in good detail of the computers there. There was a whole team of control system engineers who were responsible for the HMI graphics and the control logic on the controllers and the I/O and so on. But the computers it's running on were just a kind of off to the side, oh, we just built it following what the vendor said and we never touch it following that, right? And that is the basis of your asset management hole, your cybersecurity vulnerability hole that you find yourself in. That climbing out of that hole is expensive and hard and right? So it's yeah, that expertise thing definitely is needed in that space. Andrew, did you have questions, comments?
I was just going to say I'm quite keen to on the machine itself for the hosts I try and do a yum update every shutdown. Not always, not every machine, but I try and do that. And the actual build software we use, we release a new build quite often once a month or every 2 months, and try and keep all the machines up to date. And I think it's a lot of work. The advantage is if there is pain, it's a little pain. Whereas if you wait 5 years, it's a big pain.
Yep.
And maybe rolling back one month is easy. Rolling back 5 years might be really hard.
Yep. There's some geometric or exponential growth related to that, right? Don't touch it for a month, it's a little bit. Don't touch it for a year, it's a lot. Don't touch it for 5 years, it's way too much.
Yeah, but that's fine where we can. But as Terry said, we've got a bunch of machines to do with our beam position and monitoring. They run Ubuntu, and the vendor said, don't do an update, you'll break the system. And what can I do? I've just got to run with the OS they've supplied us. And kind of hope we're behind a firewall and hope that does the job.
And I will say, like, there isn't an easy answer to that, right?
No, there isn't, yeah.
The answer for it in the future is a core requirement of procuring this thing to the vendor is that the vendor will deliver a solution that can be maintained, right? And we will not accept a solution that can't be maintained upfront. That's not going to fix our problem today, though, right?
No.
And fixing the problem today is the ambiguous risk management sort of piece, right? It's okay. The costs and complexities to actually patch what we have is too high. The value that this thing is returning to us in controlling the beam or the beam positioning or whatever is high. So it doesn't make sense to put the money in to replace it wholesale or whatever it is. So what other options do we have to mitigate risk? And this then comes into things like, can we appropriately isolate and segment the network that it's running on? Can we apply other kinds of controls to it? So maybe the operating system itself is unmaintainable or whatever. Is that virtualized? Is that contained and isolated away from other assets and other things? Maybe, I don't know. The big piece there is really network isolation, zoning, segmentation, that kind of thing. And what other controls can we use?
Unfortunately, Epix, well, I think there's ways around it, but Epix doesn't lend itself to zoning.
Yep.
Like that. It likes.
So zone away the entire synchrotron.
Yes. Anyway.
There's also the manpower aspect. I mean, if you wait till a shutdown and then do a YAM update on everything and it breaks half a dozen things, there's no time to fix all the things, the non-cybersecurity things that the Beamline needs done in that period.
Oh, that's true, Terry. And I mean, touch wood, when I've done that, it's been basically painless. But I mean, you could do one host each shutdown until you get confident with it. Maybe start doing 2 or 3 at a long shutdown.
Yeah, that's a good point. And of course, forced retirement of things that have been hanging around for years and really shouldn't be there anymore or are easily replaced. That makes a lot of sense.
Just to let everyone know that the lunch break has gone from an hour now to 23 minutes.
Okay.
From an hour and a half to 23 minutes.
Okay, I'm going to get lunch.
Yeah, so we're starting the next session at 20 minutes past 1. So be quick.
Okay. Thank you all. Thank you for the invite. Happy to take more questions or whatever through email or Skype or whatever mechanism works for you. I will be reaching out to the different accelerator teams and so on in the next 6 months or so to start to go through sort of the consultation and some of the detail. So thank you all. Have a great rest of the day. Have a great weekend.
Thanks, Nick.
Thanks, Nick.
Cheers.
Yeah.
See you guys after lunch.